using generative adversarial network. So the contents are introduction, literature survey, proposed system design, results, conclusion, and references. Introduction. The synthesis of realistic image from text is an interesting and useful area, but some artificial intelligence systems are still far from this goal. So the introduction to generative adversarial network, that's a GAN model, has led to the generation of images from text, making it one of the most recent area in research. So it's very important that the generative models developed is able to mine information from text. So here we try to generate an image based on the given text description. So the given input to the framework will be an text description and output should be an image that aligns with the given text description. So this can be described by generating an image from the text description based on a generative model, and also to perform this task in a learning-based fashion based on a testing and a training data set. So in this paper, we introduce a text-to-image generation based on a knowledge graph and also a knowledge-guided generative adversarial network. And the aim is to generate images from the text description. Literature survey. The first paper is dual attentional GAN text-to-image synthesis with dual attentional adversarial network. So in this paper, the author tries to introduce a dual attentional module that is able to enhance local and the global structures, and the dual attention modules are mainly the textual attention module and the visual attention module, and it also uses attention embedding module, and the inverted residual structure is used to boost the representation power of the convolutional neural networks. The second paper is a query is GAN scene retrieval with attentional text-to-image generative adversarial network. Here, the author introduces a query is GAN framework, which is used for scene retrieval performance. It consists of two phases, query image generation and estimation of relevant scenes. It uses a attentional GAN model for the query image generation. Third paper of literature survey is instance mask embedding attribute adaptive generative adversarial network for text-to-image synthesis. Here, the author introduced a framework called the instance mask embedding and attribute adaptive GAN model. And here it also uses the techniques like box regression, global generator, instance embedding, and adaptive discriminators to synthesize the exact visual attributes. Attentional generative adversarial with representativeness and diversity for generating text to realistic image. It uses a RD attention GAN to generate images from the text and uses a multi-pair generators and the discriminators, and it mainly focuses on the representativeness and diversity of the generated image. The fifth paper is GAN++ realistic image synthesis with stacked generative adversarial network. It consists of a two-stage stacked GAN model containing of stack GAN version 1 and version 2. Stack GAN version 1 is used to produce low resolution image, and stack GAN version 2 to produce high resolution images. Sixth paper, generative adversarial zero-shot learning via knowledge graph. And here it introduces a zero-shot learning and a knowledge-guided generative adversarial network that incorporates the knowledge graph with the generative model. So here it uses a graph neural networks and encodes the knowledge graph from two views, that is a class view and the attribute view. So the model generates images from the unseen classes based on the given knowledge graph. Proposed system design. So it's the overall design of the proposed model consists of two sections, knowledge graph building, and the other one is a knowledge guided generative adversarial network. So the two modules, knowledge graph and the KG GAN, consists of the graph convolutional and the GAN model. Then it is a representation of the proposed knowledge graph model consisting of knowledge extraction and the knowledge fusion. The knowledge graph is mainly used to mine information from text, and it is represented based in the forms of nodes and edges. The input to the knowledge graph building is a text description, and output should be a knowledge graph based on the given text description. There are mainly two modules, that is the knowledge extraction and the knowledge fusion. Knowledge extraction phase consists of sentence segmentation that splits the given text into small sentences. It uses the method called tokenization to identify tokens, and also shortlists a sentence that contains only one subject and the object. The next section is entity extraction. It is mainly used to identify the nodes from the text description, and the entities are nouns, proper nouns, compound words, etc. The main methods used are parser speeching, tags, dependency parsing, entity recognition, and the nodes generated are represented as subject and object. Relation extraction, it is used to identify the relation between the subjects and the objects, uses a method called dependency parsing, and it is represented as an edge between the subjects. So output from the knowledge extraction will be the subject object along with the relation. So in the next section, knowledge fusion, it takes the output from the knowledge extraction and mainly consists of the sections like data integration. It represents extracting information on a standard called RDF and combines data from different resources and provides a unified view of data. Data inference, it is to make predictions more accurate and improve the value of data over time. Entity alignment consists of two sections like pre-processing and feature matching. The pre-processing to remove the unwanted noise and features, and the feature matching to align and identify single objects. Ontology construction, it is used to represent the extracted data in the form of SP or triples, and it also identifies the root. After identifying the root, it attach the identified subject, predicate, and object to the root node, and the subjects and the objects represent as nodes, and the relation is represented as edges. This representation of nodes and edges is classified as a knowledge graph, and the quality evaluation is used to identify the quality and accuracy of the graph generated. So the next coming is a knowledge GAN framework consisting of graph convolution networks and the generator adversarial network. The knowledge graph framework is mainly used to convert the knowledge graph to an image, and the input is a knowledge graph. So here it uses a graph convolutional networks that is used to convert the knowledge graph into its identical embeddings, also known as low dimensional vectors. And it consists of three layers: input, hidden, and the output layers, which is used to propagate the dependencies from the knowledge graph. And results from the knowledge graph will be the embeddings that is based on the extracted features. The generator embeddings are given to the GAN model that consists of two networks, mainly the generator and the discriminator. The input to the generator is the graph embeddings and the random noise. And based on the given input, the generator tries to generate images. So the embeddings and the generated image from the generator is given to the discriminator. And the discriminator check whether the images given by the generator is real or fake. This is done by achieving the discriminator based on a training data set. And the generator is also trained based on the given discriminator, and the evaluation is based on the cost function, where the cost function propagates the values generated by the cost value to both the generator and the discriminators. And the values given will be in the sets of 1 and 0, but it does not mean the exact values 1 and 0. It means between 1 and 0, and the most realistic to 1, it is given as a real image, and most equal to 0, it is given as a fake image. So the data set here used is a Caltech USD birds data set. It consists of segmentations and images of the birds, consists of 200 classification of birds and 1100 and 788 images. It includes 15 power locations, 312 binary attributes, 1 bounding box as annotations per image. For each image, it contains 10 single image descriptions, and the training consists of 5,994 images, and testing set contains of 5,794 images. So the result, so the input given the text and output generated is the image, and the generated image is of high resolution, realistic, matching the description, and able to attain the global and local features. It performed with an inception score of 4.84 plus or minus 0.4. So it is the output result from the model, and on the left side it gives a description of the text, and on the right it shows a knowledge graph being generated for the text description and the image being generated from the given knowledge graph and the text description. This graph represents the embeddings generated from the graph convolution networks based on the knowledge graph, and it represents the extracted features of the knowledge graph. Conclusion, so it's a recent development, and in this paper we introduce knowledge graph and the knowledge graph generated adversarial model that uses graph convolution networks and the GAN model. So these are the references. Thank you.
This is one of the most upcoming area where we basically interact to the systems. So it was a very a very good proposal. So I just have some queries. Can you explain on graph convolution models?
Yes, sir. Here we are using a graph convolutional model. It's mainly used to convert the knowledge graph generated from the text description to its embeddings. Embeddings mainly use the low dimensional vector representation. So whenever we have extracted informations from the text, these text informations are represented as a knowledge graph as nodes and its edges. So these edges are given a particular value, and these values are represented as embeddings in the graph convolution network.
For each image or for each data set that was you are trying, there will be a lot of information that need to be, or there is a lot of metadata coming along with that, right? Then only we will be able to assimilate the results. So have you faced any issue with the memory or allocations?
Um, Actually, I face difficulty in memory when we give many times of training time. If the allotted time is more, it also take more time to get for the training time. And the memory is also, when it comes to high training times, the memory is also is a difficult problem.
So have you any alternate idea on how it can be remedied or checked?
No, sir.
Okay, just try working out using hashing. Okay, so it is one of the most commonly used technique in order to sort such sort of issues. Okay. Also, that's all from my part. Also, you could have double check for your presentation for spell checks, typos, and the many contents were not that much aligned. When you
Yes.
come for the presentation, just try to look on that.
Yes, actually, in my it was correct, but when I download, I think
Yeah,
the
fine.
format
I
has
will
come.
just take. Okay, thank you.
Thank you, sir.
Next, I call upon paper ID 133 to present AI Farm, a crop recommendation system. It's an online presentation. Now I call upon paper ID 133 to present AI from a crop recommendation system.
Hello.
Yes,
Am I
you are.
audible?
Yes, you are.
Yeah.
Please note it's a 10-minute presentation. You may start.
Yes. Good afternoon, everyone. I'm Abhinav Sharma, and along with me are Muskan Bhargav and Akshay Khanna. Our team is here to give a presentation on proposed topic, AI Farmer Crop Recommendation System. Coming to the introduction, contributing to about 17% of Indian total GDP and providing employment to more than 60% of our net population, crop cultivation or agriculture plays an essential role in the Indian economy. With the advent of technologies like vertical farming, etc., evolution in this domain has been pretty evident. But when farming has such a massive command over the country, Indian farmers still rely on conventional methods and beliefs in order to exploit their land. Depending on the weather to comply with their farming method, for instance, and not vice versa, is something which is found in every farmer's traits. The intent of our research is to make possible crop suggestions for farmers by predicting which crop suits their situation and surroundings the best. Through an analysis of influential factors such as composition of nitrogen, phosphorus, potassium in the soil, the pH value of soil, humidity, and rainfall. Using various models, namely decision tree, Gaussian Bayes, logistic regression, random forest, and an ensemble model XGBoost, which falls under the domain of machine learning. Deployment has been done on an Android application using TensorFlow Lite to ensure accessibility and ease to use for all the farmers and at their fingertips. Now coming to the dataset used. The dataset is created by collecting data from sensors installed on different farmlands for 22 different crops for the whole year across different states. The size of the dataset is 2,200 rows and 8 columns, namely nitrogen, potassium, phosphorus, rainfall, humidity, pH level, and crop. The detailed distribution of data set according to the crops is in table. Now coming to the contribution, there are various researches that have been carried out previously with a similar intent as ours, but this is how the research carried out by us stands out. We have created a data set by augmenting data sets of rainfall, climate, and fertilizer data acquired using sensors from various states of India and with respect to 22 different crops types for an entire year. Also, we are deploying it on an Android application that connects us to a network of farmers. Coming to the feature extraction, we have 6 different features that affect the output of our model, and hence we check for correlation among these features for 2 reasons. First, to detect and avoid outliers, and second, to check if there is a feature that might extensively or negligibly affect the output. Pairplot is used for this task. It allows us to analyze both distribution of single variables and relationship between 2 variables. In the next slide, you will see the pairplot generated. This is the pairplot that we have generated, and here we see for feature correlations. Coming to model architecture, the dataset is distributed in 80 and 20% for training and testing respectively. Before giving the prediction models and dataset input, we perform random oversampling on the dataset with random state value too. We have applied 5 different machine learning classification models, namely Gaussian naive Bayes, decision tree, logistic regression, random forest, and XGBoost. Coming to resultant analysis, after all the models are trained, they are evaluated by first passing the test data to the model, and then the output that is generated by this is compared to the labels of the test data set. These models are compared by evaluating various metrics like accuracy, precision, recall value, ROC, curve, weighted harmonic means of precision and recall, and F measure. This next slide, this is the confusion matrix for Gaussian naive Bayes. Next slide, this is the decision tree for, this is the confusion matrix for decision tree. The confusion matrix for logistic regression. The confusion matrix for random forest. And finally, our ensemble model, the XGBoost. And here we analyze it after evaluation metrics of all models. It can be seen that decision tree and logistic regression perform almost identically. Gaussian naive Bayes, random forest also have almost identical performance, and XGBoost outperforms rest of all the models by minimum loss. Coming to prototype design. This is a prototype design for a mobile application. Deploying the saved model files in Android application will help farmers to easily use the application by just giving the required inputs and getting crop recommendations. Inputs to be passed by the user are nitrogen, phosphorus, potassium, and pH value of the soil at that instant. The saved model file is of 149 KBs, and the Android application works with internet connection. This makes the system scalable and helps the application to run on low-end configuration devices. The saved model is converted into a TensorFlow Lite file and executed by TensorFlow Lite interpreter. Now the limitations of our project. As fascinating as the research is, there are few areas where our work falls short. Among the factors which we have chosen for evaluation and prediction, temperature is not one of which is another element which has a major impact on the growth and yield of a crop. Amount of irrigation is another factor which affects cultivation, which has not been accounted here in the research. And no study on pest and their influence has been done. We are incorporating these modules into our further research. Coming to future scope, there are a lot of sectors in which this work, whether development can be carried out. For instance, considering the soil type in dataset, suggestions based on amount of irrigation and the amount of fertilizer and its type can also be indicated. Inclusion of a pest detection to minimize the damage in crop yield can also be carried out. Hence, we propose a complete ecosystem of AI in farming where the suggestion of crop, suggestion of fertilizer, suggestion of how much irrigation should be done, the temperature that should be maintained. And by using computer vision, we can detect the pests on the crop leaves, hence maximizing the yield. To conclude, from this entire study, we draw out certain conclusions. Using ensemble model increases the accuracy and decreases the error rate. In this paper, we have used XGBoost as an ensemble model. Different soil types support different crops, which justifies the error rate in models. Saving the models as pickle files, which is a standard way of serializing objects in Python, helped in easy deployment and real-time usability. Thank you. That was all from our side.
I hope I'm audible.
Yes.
Okay, there have been a lot of innovation happening in AI in the area of agriculture.
Yes.
So, just in very brief, can you just tell me what makes your work unique? Because we have a lot of recommendation system, lot of Android applications running. So, what exactly makes your system better when compared to others?
So two things. First, we have taken crop data from 22 different states using our own hardware components. So, and we have removed the outliers and also the redundant data. That decreases the error rate. And second, the deployment that we are proposing in an application which has the low end with low end connection configuration devices where there is no connection, there is no need of internet, makes our application unique.
Okay,
It is a one.
yeah, I got it. But what I wanted to suggest is we have now end-to-end services available, right from
Yes.
an IoT-based farming, where you get all the data which we need to manually, and it can be taken directly from sensor, right from the crop selection to what type of fertilizer to use, the kind of watering that need to be done, to
Yes.
the market study. So lot of things are there. So this is just my suggestion. If you can come up with a general framework where you can include the machine learning, the computer vision based pest analysis, the kind of disease that a particular leaf is having, so that might make your study more interesting. So that was just my suggestion from my part to if you can develop this as a general framework, so that will be much given you a much better lead on the particular study. Okay, thank you.
Yes, sir. Our further research is inclined to this. So we have started with fertilizer uh, suggestion and yield predictions, and now then we'll move on to pest, and then we'll make a complete ecosystem where there will be a common dashboard for all these things.
Okay, thank you, thank you.
Thank you, sir.
Next, I call upon paper ID 81 to present flood detection using deep learning. Please note it's a 10-minute presentation.
Okay.
Good afternoon. My topic is flood detection using deep learning. Oh. Miss Lakshmi here, ma'am. Miss Lakshmi here.
Hello, Madhu sir. Can you hear me? Hello, Madhu sir. Hello, Madhu Mutur sir. Can you hear me?
Yeah,
Okay,
so
sir.
audio issue. Yeah, I'm able to hear you.
Okay, good afternoon, sir.
Good afternoon. How is the conference going on?
Yeah, going on fine. Okay, you have few more minutes. We'll start shortly.
Yeah, sure.
IIT Madras, working as a professor. His current interests include computer architecture, mainly focusing on heterogeneous computing systems, multi-core architecture, interconnection networks, and secure processor microarchitecture. He is associated with programming languages, architecture, and compilers education lab. He is also a senior member of IEEE and ACM. We are indeed honored to have such a distinguished speaker with us today, who will be joining with us on Zoom meeting. May I take the pleasure inviting Dr. Madhu Mutyam for his keynote session.
Yeah, thank you very much for the introduction. And good afternoon, all of you. So let me share the screen. Okay. Right. So next 45 minutes or so. So I'm going to talk about the unified memory in heterogeneous computing systems. And first of all, I'll explain like what is an heterogeneous computing. And for that, we'll start with multi-core systems, move to GPUs, and then come up with an heterogeneous computing. And then we'll see what is unified memory, what are the opportunities and the challenges that are there. And at any point of time, if you have any questions, you can interrupt me. So we know that the computers are classified into 4 categories. There's a Michael Flynn's taxonomy of computers, if you consider. These are actually based on parallelism that is available in applications. We can have instruction level parallelization, we can have data level parallelization, and we can also have task level parallelization. When I say instruction level parallelization, basically within a program, we may have independent instructions together. And so if that is the case, then we can execute these instructions in an out of order fashion based on the available functional units in the processor. And all our current processors, if you see Core i7 processor, i9 processor, or AMD processors, and so on, individual core is actually exploiting this instructional parallelization and executing the instructions in out of order fashion. And we also have parallelism at the data level. That means the same instruction may be executed on multiple data items simultaneously. A simple case is, let us say we are working on a vector, a set of vectors. Let us say 2 vectors are there. We want to add elements of those things and return to another vector. So here we have a single add instruction, and that will be performed on each element of this vector. In other words, if I just have, let us say, 2 arrays are there, and then I want to add element by element of one array to the other array and store the result in the third array. So which, if we generally use a normal processor, then it will be like we may have to write a for loop for I equal to 0, I less than 100, I plus plus, C of I equal to A of I plus B of I, right? But if you have a processor which is actually exploiting this instruction or data level parallelization, we can simply have one instruction, which is like C of 0 to 99 equal to A of 0 to 99 plus B of 0 to 99, which is like, this is called as a vector instruction, which is operated on a set of elements rather than a single pair of elements and so on. And we also have in the applications the task level parallelization. That means a single application, maybe we can construct that into a parallel, the set of parallel processors, and each of those things can be simultaneously executed on available hardware components also. Because now the applications have these type of parallelism, either at the instruction level or data level or task level, we need to have associated hardware to exploit this parallelization. And that is where we have this unicore processors, GPUs, multi-core processors, and so on. And based on this, Michael Flynn has given a classification of computers. And the first one is SISD, single instruction, single data, where every time we'll be taking one instruction from the instruction pool, and that will be executed on a pair of elements from the data pool. And this is where such type of processor where we have this instructional parallelization exploited. And the examples for such processors is uniprocessor system, or otherwise if you consider a multi-core system where individual core is part of this particular scenario. And then we have this SIMD, where a single instruction and multiple data. So we'll be taking one instruction, but we'll operate this instruction on multiple pair of data items by sending this to multiple processing elements. And the example here is a GPU. Or we can also have normal CPU processors with multimedia extensions in their ISA and so on, or vector architectures. All these are examples of SIMD type of computers. And then we have this MISD. Of course, there is no commercially viable implementation for this MISD. MISD says like multiple instructions are going to be operated on a single data item, which is actually, there is no practical application for such type of things. So there is no processor designed for this type of classification. And then the last one is MIMD, multiple instructions and multiple data. So here we'll be taking multiple instructions from the instruction pool, and each of these instructions may be operated on multiple data items. And this is where you can see here, a lot of processing elements are there, and they'll be performing either same instruction or multiple instructions simultaneously and so on. And an example for that is our current day Core i7 processor, for example, or AMD processor, EPIC processor, whatever. If you consider such type of things where we have multiple cores on a single chip, where these multiple cores are independently working and parallelly they are working. So that means if you have a multi-threaded application, multiple threads can be mapped onto this multiple cores, and each of these cores is simultaneously working along with other cores and so on to improve the overall throughput. It's not necessary only multi-threaded applications running on a multi-core. You can also have a multi-programmed workload. That means independent applications can run simultaneously on multiple cores and so on. And such type of processor actually exploit the thread level parallelization, parallelism that is available at the thread level. And Core i7, such type of processors are examples for tightly coupled MIMD, or we can also have a loosely coupled MIMD, multiple instruction, multiple data. Loosely coupled means like externally we can connect multiple processors together to make this into a multiprocessor computing system. Or we can also have warehouse scale computing, large set of processors sitting in a data center where our requests can be sent to the data center, and the data center will process the request and then send the result back to us. An example is, for example, Google. So millions of users may be using Google simultaneously, and then they will be sending their requests, and all these requests will be sent to these data centers where they will be processed, and then the result sent back to the requester. And that is what is request level parallelization. So these are basically the, if you see the spectrum of computing systems these days, we have the uniprocessor systems, we have multi-core systems, we have GPUs, we have large scale computing systems such as warehouse scale computing and so on. And each of these systems are exploiting parallelization available applications at different granularities. Either it may be at the instruction level, or maybe at the data level, or maybe at the task level and so on. So now, if we just look at the 40 years or 40, it's more than 40 years, okay? So it's a 40 plus years of processed data if you look at. So the number of transistors integrated on a chip increased significantly. So if you see from 1974 or 75 time frame to the current day, so we have large number of transistors in a single chip. Can anyone tell me the number of transistors that are there currently in any of the latest processors? Just can someone guess the number? How many transistors that are going to be there, that are there currently in the processors chips? So it will be like billions of transistors. So billions of transistors are integrated in a single chip. But once we have these billions of transistors, what is the use of that? Where do we require to use all these things, right? So generally what we do is, once you have large number of transistors, now we have the flexibility to provide variety of functionalities. And that is the reason why now these days, if you see, even in a mobile processor, a processor in a mobile device, cell phone, we have like octa-core. So multiple cores can be placed inside a single chip, so that multiple things can be executed simultaneously. Or we can dedicate some transistors for processing or providing some accelerators, a GPU accelerator inside a general purpose system. So we have like, or we can have some of the transistors can be used for audio processing, video processing, and different type of things we can provide. That means once you have this large number of transistors available to us, then we can provide different functionalities requested by the user. And because we are actually going ahead with large number of cores and so on, and also each of these transistors are clocking with higher frequency. For example, if you see this frequency curve, so it started with merely few kilohertz frequency, all the way up to these days we have like gigahertz processors. So we have large number of transistors that are there in a single chip, and we have all these transistors clocking with gigahertz frequency, so which is going to result in a significant performance, and that is what this the second curve shows, right? The second curve shows that the single threaded performance also significantly improved over a period of time. But if you see here up to 2003 or 2004 time frame, everything was like going significantly in a good integration of transistors would at the high rate, and similarly the performance was going up the high rate, and the frequency scaling is also happening the high rate up to 2003-2004 time frame. But after that, from 2004 onwards, if you see the frequency scaling is almost flat. That means not much improvement in the clock frequency. And because of that, the performance is also not improved as that of the previous period, right? Here, almost like it's roughly, we are getting around 50% improvement in the performance and so on, but here it's roughly 25% or something. But the transistor scaling is still happening and so on. Why there is a flat in the frequency curve here after 2004? That is because once you have billions of transistors or multi-millions of transistors clocking with a higher frequency in terms of gigahertz, so the typical power consumption is also increased significantly. Once the power consumption, because once a transistor is switched, right, then automatically it is going to consume power. And when you have only few transistors are there, the power consumption is not much. But if you have billions of transistors clocking with a higher frequency, it is going to consume significant amount of power. And once too much power is consumed, power per unit area is called as a power density. Power density is going to increase because your chip area is not increasing. Once the power density increases, power density is translated to heat. And heat is nothing but the temperature rise on your chip. Unless until you have a cooling technology to cool down or dissipate the heat generated on the chip, so you cannot clock your processor with higher frequency and so on. You have to stop working and then you have to cool down the chip so that again you can start reworking with that and so on. And because the cooling technology is not improved that significantly, so as a result, they decided not to scale the frequency and they were just maintaining the frequency almost like a flat. And this is mainly to constrain the overall heat generated on the processor, to reduce the heat generation or to reduce the temperature increase on the chip because of not having good cooling technologies to cool down the chips and so on. And that is where actually they started thinking about, rather than just going ahead with a single core with aggressive superscalar processing out of order execution to improve the performance and so on, then they decided to go for increased number of cores rather than improving the complexity of or improving the performance of a single core processor. So this is where, like, if you see around this time frame, 2003-2004 time frame, they started looking at a multi-core processor rather than uni-core processor. So until this time, the number of cores were like only one. But then from there, the number of cores is scaling up. And now these days, we have like hundreds of cores on a single chip. And once you have this hundreds of chips or hundreds of cores in a single chip, again, you can improve the performance. But of course, each of these cores can work with a lower frequency and so on to handle the power generated, power consumed on that particular core and so on. So basically, and in addition to this, there's also another important problem that is called as memory wall. Okay, so which is nothing but the processor performance improved significantly, but the DRAM performance is not improving much. Let us say if I give you 100 processors, 100 cores on a single chip, and I ask you to run, okay, 100 threads, map 100 threads onto this 100 cores and then execute something. But what is going to happen here is, if you have hundreds of cores, all these applications running on these hundreds of cores, they require the data. But where do you get the data? Data is there in the main memory. And if main memory performance is not improving, even if you have large number of cores, and if the data is not supplied to the threads running on these cores, then the overall performance is going to be degraded. That is what is called as a memory wall problem. Memory performance is not improving as that of the processor performance. So we need to come up with some mechanisms to bridge the gap between this. So that means there are many techniques proposed, for example, cache hierarchy and other things and so on. People propose to bridge the gap between the performance gap between the processor and the DRAM based memory. But keeping all these things, now the trend is going for large number of cores rather than a single core with the complex design. So there is a change in the paradigm from a single core to a multi-core. And so I'll just pictorially show what is the benefit of multi-core. Let us say we have a single core processor with a complex design, and it is giving you 1 unit of performance and consuming 1 unit of power. And this color shows like this is very complex design, verification cost is too much, design cost is too much, and so on. And is also going to run with a higher frequency and so on to get 1 unit of performance. Now we can go for a simple design of a processor, and we can run with lower frequency, not deeper pipelining, not aggressive superscalar and so on. But because of all these simple designs and so on, then the performance is also going to be degraded compared to this one. This is a 1 unit, but here it may be less than 1 unit, roughly like maybe 0.6, 0.7 times of the original performance. But because it's running with a lower frequency and the lower supply voltage, power consumption also reduced. But now if I design this processor, no one is going to buy because this is performing inferior to the previous design. Now what I have to do is, and also you can see here, this is taking 1 unit of area, but here it is taking only 1/4 of the area as that of the original processor. Now what we can do is we can actually replicate this design. Once we design, then we can replicate multiple times. It's almost like our software code. When we write one function, the same function can be used in multiple places in our applications and so on. Similarly, here also, once you design and verify, the same design can be replicated in a number of times. And now once we keep it 4 replicas of this particular thing, it is taking almost the same area of this, and the power wise, it is almost consuming the same amount of power, but the performance is improving. And if you see here, individual cores are running with lower frequency than that of this base design, but the performance is improved. That is because multiple threads are executed simultaneously on this particular thing. Whereas here, a single thread is going to be executed and so on. So the idea is, don't go for a complex design, go for a collection of simple cores. So multiple slower cores are better than a single faster, powerful processor. And that is what the current trend in the processor industry, and everyone is actually going for increased number of cores to improve the overall performance. And if you just see the block diagram of a multi-core system, if this is basically a single core processor, consists of your processor, functional units, register file, and bus interface connected to the rest of the things. And you have IO bridge, which is connected to IO bus, and for which there are multiple device drivers are there, which are connected to USB port, the graphic adapters, and hard disks, and so on. And this IO bridge also connected to main memory. This is basically a single core system. But if you consider multi-core, the equivalent one will be something like this. So I'm just going to show only this part, and the rest of the things will be shared. Only this part, instead of a single core, now I have multiple cores on a single chip. That is the reason why it's called as a chip multiprocessor. 4 cores are there, and they are connected to this bus interface. And any of these cores wants to communicate to this memory or disk or whatever. So they will place the request on this bus, and through this, it will be connected to this IO bridge, and rest of the components will be connected to that. Okay, so this is basically like, if you see internal inside our Core i7 or i9 processor, something like this will be there. In a single chip, we are going to have multiple cores. So if you look at some of the latest multi-core processors, so we have IBM Power 10, which has like 16 SMT, simultaneous multi-threaded processors, and each SMT core is actually having 8 logical threads. Basically, it is now the total number of threads that can be executed simultaneously is 8 into 16. Right? It's huge, 128, right? So those many number of logical threads can be simultaneously executed on this single processor, IBM Power 10. If I look at Intel, so there are again large number of cores are there, and so each core is again a multi-threaded processor, and one core to another core will be communicated through this interconnection network, a mesh type of topology, and through that, an application running on this core can communicate with an application running on this, or it can communicate with the memory controller connected to this memory controller, and so on. Anyone can be connected to any other things and so on. And if I just look at AMD, then we have, for example, here you can see there are eight core clusters, and each cluster is having 8 cores. So effectively 64 core multi-core system from AMD. So basically, if you see, these are some of the latest processors from different processor vendors. And if you see, tens of cores are interconnected on a single chip. And if they want more number of cores, then they can actually have multiple chips connected with the socket communication and so on. And then you can place multiple chips on the motherboard, and through that you'll increase the total number of cores. So all these are basically from the CPU side. Central processing unit, basically previously used to say, but now we can say it's a processing unit which is going to perform general purpose computing. But we also have the other part, because all these are actually exploiting the instructional parallelization and the thread level parallelization. But we also have the data level parallelization, right? And if you see that, so we have corresponding hardware components which are graphic processing unit, GPUs. And there are, again, the graphic processing units mainly designed for handling this graphics related stuff, where we'll be operating at the pixel level, and multiple pixels we can operate simultaneously and so on. So that is the reason why they exploit the data level parallelization. And most of our process computers, whether it's a desktop or the laptops, we can also have the graphic cards, and which are actually taking care of processing any graphic related. If you are playing some video game or something, typically those things will be processed by the graphic card associated with our computer. And these are massively multi-threaded many core chips. Thousands of cores are going to be there in a single chip for these graphic processing units. And if you look at some of the latest graphic processing units, so one is from the Nvidia GeForce RTX, so which has like 10,000 plus CUDA cores, and each core is running with 1.4 to 1.7 gigahertz frequency, and it has like total main memory, GDR based main memory, which is of 24 GB capacity, and it provides good memory interface and almost like 1000 Gbps memory bandwidth it provides. And we also have from AMD Radeon is also another graphic processing unit, which has like 80 computing units, and each computing unit has large number of streaming processors. Basically, it is going to have a total of 5,120 streaming processors. And again, they'll be running with gigahertz frequencies. But if you see here, compared to the CPUs, we have like roughly tens of cores or maybe hundreds of cores, but here we have thousands of cores. The reason is here thousands of cores are there, but each of the core is a simple core compared to the CPU side of things, where each core is like a complex one, which is going to process big computations and so on. But whereas in GPUs, it's a simple pixel level computations and so on. Maybe a few additions and multiplications type of things and so on. So not much computations required here, but they'll be working on large amount of data simultaneously. So if I just look at one of the latest Nvidia GPU processor, so Nvidia Ampere architecture, if you see, so here it has like, so 128 streaming multiprocessors, and each streaming multiprocessor has large number of the cores, where it has like a tensor core and set of functional units for integer operations, floating point operations, and lots of things are there. And it also has the level 0 cache, level 1 cache, and then the shared L2 cache, memory controller, which is connected to the GDR based, the global memory, and all these are the streaming multiprocessors are, they can access the data from this global memory or the shared L2 through this interconnection network. And basically, if you see here, so it has like a register file. In the normal CPUs, we have register file with maybe tens of registers, right? If you consider temporal registers or the architectural registers, which are like very few. But here in GPUs, we have thousands of registers, but very less control logic required in GPU type of things, because data dependency among the instructions is very less in GPU applications compared to the CPU applications. Now, if you put together back to back the CPU and GPUs, then yeah, anyway, so let me first focus on the GPU programming part. So how the programming on the GPU is going to be done is, we have this, for example, if you see the Nvidia architectures, so we have this CUDA, Compute Unified Device Architecture, defined by the Nvidia. And if you're using Nvidia chips, then we have to use this CUDA. That means we have to program using this CUDA platform. Or if you are using, there is also an open source programming environment for programming with the GPUs, that is called as an OpenCL. So we'll be using these programming environments to code and then execute our code on the underlying the hardware, the GPU architecture. So what is actually happened is, so we have these GPUs in our computers working as an accelerator. And anytime, if you want to float or if you want to run some computation on GPU, first we have to start that with the CPU. So CPU is going to offload the code and the data or the memory to the GPU side, and then the GPU is going to start executing on it. So basically, this is called as the host, and this is called as a device. So from host, we are sending the data and the code to this GPU, and the GPU is going to execute. And there, because we will be using this CUDA or OpenCL platform, and also the programmer has to specify how much amount of memory is required for this computation, and he has to organize the computation component also into a set of grids, and each grid consists of a set of warps and so on. All these things the programmer has to configure. The program has to design, and then he'll send this entire code offloaded to the GPU, and the GPUs start executing the things. And once the GPU completes the computations, then the results will be sent back to CPU side. So CPU is acting like a host and GPU is acting like a device. So now if you see, basically we started with the CPUs, where all the cores are of the similar structure, the homogeneous setup. Then we also have, now there is a GPU. So CPU is working for the instruction level or task level or thread level parallelization, and GPUs are working for the data level parallelization. Now we are going to put all these things together, CPU and GPU, to make this as a heterogeneous computing unit. Now, if we just compare the performance point of view, both the CPUs and the GPUs. So CPU are typically like, we have few number of cores, and we have large amount of chip area is covered by this caches, L1, L2, L3 caches, and then outside we are going to have this DRAM, which is also one of the parts in the memory hierarchy. And whereas if you see the GPUs, so this each is small piece is actually the processing element or a core. We have large number of cores, and we have some amount of L2 cache and the DRAM memory. But if you see here, L1 cache is very small. And here in the CPU side, we have good amount of chip area is dedicated for the control unit. But whereas in the GPUs, the control unit is very small, because the data dependency is not much, and we don't have to actually come up with a complex control unit design and so on. So because we are reducing, cutting down the control unit space and so on, we are using that for adding more and more simple cores on the GPU side. So now, if I compare these two designs, so if you see the performance point of view, so double precision, the floating point operations, if you see, so the GPUs obviously are going to give a significant performance. And that is mainly because you have large number of cores running simultaneously. Of course, this will be, again, this is mainly for the applications which are exhibiting high data level parallelization. But if you are looking at the normal general purpose applications, we may not have so much data level parallelization. So if we consider applications consisting of some data level parallelization, some task level parallelization, the instruction level parallelization, and so on, then we actually, it is good to have a design, a single processor consisting of collection of CPUs, collection of GPUs together. And that is where we are actually coming towards heterogeneous computing. And these days, now the trend is going for heterogeneous computing rather than homogeneous multi-core type of system designs. So this is what this slide is going to say, whether always the homogeneous cores are good, or do we have to have heterogeneous cores? And for that, we can actually consider this Amdahl's law. Amdahl has given an interesting formula. It says like the overall performance you can get from your underlying multi-core system is determined by the sequential portion that is there in your application. If significant percentage of your application is sequential in nature, even if you get thousands of processors, your performance is not going to be improved. That is what this formula says. And if you give some numbers to this and then plot a graph, it will be something like this. You can see here, even if my application has 95% of the code, or even if my application, 95% of the code is parallel, that means only 5% of the code is sequential. Even then, if I get 65,000 plus number of cores, I'm going to get a speed up of only 20x. So this actually says that your application overall performance is determined by the parallel portion that is there in your application. Of course, after this Amdahl's law, there is another law proposed by Gustafson. And according to Gustafson's, if you have large number of cores, why do you want to execute only one application? Why can't you execute multiple applications so that your overall throughput is going to be improved? And that is where like actually the current multi-core systems are actually doing like that. It's multi-programmed workloads can be executed simultaneously on a multi-core system. But from this slide, actually, one point we can see is rather than going for a homogeneous multi-core processor, we can have an heterogeneous computing system consisting of both the CPUs and GPUs together. And if you just look at one of the latest heterogeneous computing processor, which is from Apple M1 processor, consisting of CPU cores, GPU cores, and also a neural engine. This is mainly for running your machine learning algorithms. And this CPU is for general purpose applications, where even in this 8-core CPU also, they are considering 4 complex cores and 4 simpler cores. And then there is like 8-core GPU for running any graphic applications. Now, if you see this in a single chip, you have different type of things together. If you have normal applications and if you want to execute them in a shorter period of time, then go for this complex cores. Otherwise, like normal application, but not so important for executing quickly, then maybe you can run it on the CPUs with a slower frequency and so on. Or if you have a graphic running some video game or something, then maybe executing that on the GPU core. And if you have some learning things you want to observe and so on, maybe such type of things can be executed on this neural engine and so on. So now in a single chip, now you have all these components. Basically, it's called a system on chip type of thing, where consisting of processing general applications, processing graphic applications, and running some machine learning algorithms together. So basically now we have the system on chip with different functionalities, heterogeneity in the computational capabilities. So that is where they also actually come up with an interesting idea of unified memory. What is this unified memory here? So far we discussed that it's not a good idea to consider homogeneous cores, go for heterogeneous cores consisting of different processing elements. They have specific features. They'll exploit certain features from the applications, and they are suited for processing certain type of applications and so on. But then we also have another component, unified memory. If you just go back once, let us say here, if you see here, I said GPU is working as a device and CPU is working as a host. Always your application, graphic application also starts from CPU, and it is going to offload the data and the code to the GPU, and GPU is going to execute and then send the result back, right? So basically what is going to happen is here, everything memory is under the control of the CPU, and this is going to send the set of the data and so on to the GPU, and GPU is going to execute. Whenever GPU incurs a miss for some data or something, again, it sends the request back to this, and then the CPU is going to send the chunk of data. So everything is controlled by CPU. But now if we consider unified memory, the idea is an application running on this core can access the memory associated with this or associated with this or with this. Anywhere it can access the memory. And similarly, an application running on this can address any location from the memory associated with the CPUs, GPUs, or whatever. This is basically called as memory is unified. It is not just, okay, the CPU memory, GPU memory, and so on. A CPU can access the data from the GPU memory, or GPU application can access the data from the CPU side memory and so on, because it's a unified. Everything can be seen from anywhere. And once you have this unified memory, so the programmer's effort is going to be significantly reduced. And that gives a more flexibility to the programmer. So he can just focus on writing the code, and then the application can run efficiently on your associated processing elements and so on. So if you just look at the memory hierarchy from the CPU and the GPU side, that means on a heterogeneous computing platform. So in CPUs, we have this multi-levels of caches, main memory, and the secondary storage. And if you have the GPU also along with this, then this has like streaming multiprocessor and shared memory, L1 caches and so on, and shared L2, and then the global memory, that is a device memory. So now, if you don't have the unified memory, basically what is going to happen is we are going to send the data, transfer the data from this to this device memory, and the streaming multiprocessors will take the data from this device memory and then they operate on it, right? So basically always the CPU is going to control the memory here, and the GPU cannot access any memory from here. And whenever it incurs a miss, it's going to send the request here, and then the CPU is sending the data back to the GPU side. So basically the communication is going to happen between this memory to this memory. That means the CPU memory, which is host memory, to the device memory. Through that, the actual communication is going to happen. And once the data is transferred, then the cores, the applications running on the streaming multiprocessors are going to access that. But if you consider this unified memory, right? So single address space across multiple heterogeneous nodes, whether it is a CPU or GPU or neural engine or whatever, everyone will see the same address space. The advantage with the same address space is like they can actually refer any location by specifying the address. Once you specify the address, then it will go to the corresponding location and get the data. And application need not worry about whether the data is with CPU or with the GPU or with neural engine or whatever. So that gives a lot of flexibility. For example, in our our CPU side multi-core systems, right? When an application is running, application can generate a virtual address. And application need not worry about where the data is located. It can be there in the secondary storage, main memory, or L1 or whatever. All it does is it generates an address saying that, okay, read the data from address X. Now this address, virtual address, is going to be translated to physical address and then go to main memory, check whether the data is there. If it is not there, it is going to go to secondary storage, get the data and put it into main memory. Of course, if you have caches, then first we'll look into caches, L1 cache, L2 cache, L3 cache, then only we'll go to main memory and so on. Basically, the idea is once you have this single address space across multiple heterogeneous nodes, any application running on any of these heterogeneous nodes can actually access this address space efficiently. And then once we have this unified memory, which is having a single address space, we are going to also consider a demand paging. What is demand paging? Demand paging is like, if an application is running, let us say in my system, my main memory is having only 16 GB of memory. But if I want to run an application which requires 30 GB of memory. I can just still execute an application which is requiring more memory than main memory capacity. That is because these days we'll be using this virtual memory concept. And on demand, we'll be bringing the pages from the secondary storage and put into the main. That means this demand paging is bring the pages on demand. Only when there is a need, you bring the corresponding page rather than bringing entire set of memory or the data for an application and put into main. You just bring only on need basis. That is what the demand paging. This is basically, you can find this in the computer organization and also in operating system concepts, virtual memory management concepts. You can go through this demand paging. Okay, so once we have this unified memory and the demand paging, so now the data management in GPUs is going to be very simple. And programmer need not worry about all these things, how much data to be offloaded to device memory and how do I organize the things and so on. Those things programmer need not worry. So application can run on the GPU, and whenever it requires some data, if the data is not there in the device memory, it is going to generate a page fault and it sends to the CPU side and it bring the corresponding page and then send it back to the device memory and so on. So the data management is going to be very simple once we have this demand paging with the unified memory. Of course, the demand paging is going to create a page fault. As I said previously, the page fault is like once an application is requesting some data and the corresponding data is not there in the main memory, that means the corresponding page is not there in the memory. So now we need to go to secondary storage and get the corresponding page and map to a page frame. So this page fault is going to be, once there is a page fault, now operating system will come into picture because page fault is going to be handled by OS. So that is going to actually take good amount of time. That is for the normal CPUs. But now once you have a GPUs and GPU side, if there's a page fault, it is going to take even more amount of latency and so on. So you need to handle this page faults also. Of course, there are advantages of data management and so on, but at the same time, there are the limitations and such things, the overheads we need to handle, such as page faults. And we also have this memory oversubscription. That means, as I said previously, right, my system has 16 GB of memory, but I want to run an application which is 30 GB of space required. So we are going to go for virtual memory concept, right? So once you have this virtual address space and you have this demand paging, so you don't have to worry about what is the amount of memory available with your system, and you can run application which requires more memory than whatever the capacity provided by the system. That is through this virtual address space. But once you have this virtual address space, then there is a problem that you need to handle, which is address translation. Because when an application is generating a request, let us say you write a program, C program, for example, and in that you declare int P. And if you try to print the address of P, right? So which is basically, it is going to generate the virtual address. But this virtual address needs to be translated with the physical address. Physical address is nothing but the address in the main memory, and the virtual address is the address in the virtual address space. Application generates virtual address. You need to translate that to go to the exact physical location in the main memory. So we need to have this address translation. So now you can see you have the advantage of oversubscription, but you have to address the problem of address translation. So how do we perform these address translations in GPUs? So if you just see a simple design of a GPU processor, so you can have set of streaming multiprocessors, consists of streaming processor, collection of streaming processors, and you have, because the moment we have address translation, each of these applications running on these streaming processors are going to generate virtual addresses, and that needs to be translated. And to translate that, so we need to have memory management unit, which consists of page tables and other things and so on. But memory management unit is going to be there in main memory, CPU side of main memory, which is going to take good amount of time. So what we are going to do is, rather than always going to the main memory to get the translated address, we'll be using translation look-aside buffers. So now the same concept, translation look-aside buffer, the page walk, all these things can be adopted in GPUs also. Because now GPUs are supported with this unified memory, an application running on this can access any address in the unified virtual address space and that needs to be translated to get the exact physical address location by using this TLB. And if there is a miss in the level 1 TLB, now we'll be going to the level 2 TLB. And if there is a miss in this, then we'll be actually going for a highly threaded page table walker. And for this, we also are going to maintain a page walker cache. A partially translated addresses are going to be cached in this page walker caches. And even if there is a miss, then we have no other option. We have to go to the CPU side and get the translated address and so on. But the address translation is one of the very important key component we need to address if we are dealing with the unified memory in heterogeneous computing systems. And that is the reason why there is a lot of interest these days from the academic community looking at how to optimize this design so that unified memory concepts can be efficiently incorporated in our heterogeneous computing systems. So GPU page faults are very costly because it is going to be handled by the CPU side, and GPU to CPU communication we need to handle, and all these things are going to incur large amount of latency. And that's the reason why we need to minimize these faults and providing efficient TLB designs, efficient page walker caches, or highly threaded page table walker. All these things we need to provide to reduce the page fault rate at the GPU side. So the opportunities available in the unified memory is, because now we have the unified memory where CPU can access any memory location or GPU can access any memory locations and so on. Now we can actually go for prefetching. For example, if you're running a GPU application on a GPU core, and maybe you observe the access patterns of these threads running on the GPU core, and then you actually prefetch the data in advance. Prefetching is like, before actually application is requesting the data, if you bring the data and put it there, when actual demand comes, then the request is going to be hit in the memory associated with that particular chip, particular core, whether it is a GPU or CPU, right? So you fetch the data so that you are going to have less amount of misses at the memory, and which is going to improve the overall performance. But when you are prefetching the pages, you have to, because your memory is limited, whether it is a CPU side or GPU side, right? So this memory is limited, but if you are going to prefetch some data, now you need to evict something else also. So you need to evict useless pages and keep the prefetched pages here so that when applications requesting the data, it can be get a hit in the memory. Of course, this is again same for the GPU side also. Here, you can evict some useless pages and bring the pages, prefetch the pages from the CPU side and put it here so that any application running on the streaming multiprocessor, which is requesting the data, and the data can be hit in the device memory rather than a miss and then going to the main memory of CPU side. So we need to, the opportunities are come up with interesting or innovative prefetching techniques, and also come up with good eviction policies so that useless pages can be evicted as early as possible. And also we may think of coming up with a compression mechanisms. Try to, because especially the GPU side applications, large amount of data can be compressed into a smaller unit. So in such cases, like if we compress the data in a given amount of space, I can actually store large amount of data. Of course, here, when you are coming up with the compression techniques, you also have to see what is the latency for compression and decompression. It should not take too many cycles. So you need to have a simple compression and decompression mechanisms to efficiently utilize your the overall memory space and so on. So we can actually look at the application access patterns, and based on that, we can actually prefetch and we can evict, and we can also do a compression mechanisms and so on. If we do all this, if we apply such type of techniques on our unified memory based systems, then we can extract more and more performance from our heterogeneous cores. So in conclusion, so especially when we are going for hexascale computing, where large amount of computational power is required, so it is better to go for heterogeneous computing consisting of GPUs, CPUs, and neural engines and so on, rather than homogeneous computing cores. And once you have this heterogeneous cores, you go for unified memory that is going to reduce the burden from the programmer point of view, and the productivity also is going to be improved. But once you have this unified memory and demand paging we are using, then so we need to handle the main issues of page faults and the oversubscription part. Okay, and these things, as long as we address, then we can efficiently utilize unified memory systems in our unified memory concepts in our heterogeneous computing. And so we need to explore innovative techniques such as prefetching, eviction policies, compression, and so on, to improve the overall performance of our heterogeneous computing systems with the unified memory concept. So that's it from my side. And if you have any questions, you can ask me. We still have another 7 minutes.
Okay. What sir? Am I audible?
Yeah.
May I know which are the different programming tools which can be applied for this type of research work in these fields?
No, what do you mean by programming tools? If you're talking about GPUs, let us say.
Yeah.
So there we have, like, because GPUs typically will be using this CUDA and the OpenCL programming. But if you are looking at the simulators, because effectively, like in the processor architecture side, if you are going to do any research and so on, you cannot change your design processor and then come up with new design and so on, right? So what we are going to do is we'll have architectural simulators. The simulators are a software program which mimic the behavior of the processor. And we'll be using these architectural simulators, and there we are going to incorporate whatever the changes we want. And based on that, we'll study whether, let us say, rather than 64 KB of cache, if I give 128 KB of cache at the L1, what is the benefit I'm going to get? For example, if I want to just see the performance from the CPU side, then I'm going to consider the corresponding architectural simulator for CPU. Let us say Gem5 is an architectural simulator predominantly used in the architecture community. And we use that to mimic the behavior of a multi-core processor and then run.
Will that mimicking be similar to the real situation?
Which one?
This simulator, can it be similar to the real situation, what is happening?
Right. So for example, even if you look at the Intel and AMD companies also, right, when they want to come up with the next generation processors and so on, so they will be using this cycle accurate architectural simulators, and they provide necessary, they change the necessary components to incorporate their ideas, and then they study the effectiveness. And if it is giving better results, then only they'll go for actually RTL design and then the actual fabrication part and so on.
So can you name that simulator?
So Gem5 is an architectural simulator. There are many similar, multi-to-sim is there and so on. Plenty of simulators are there, but Gem5 is actually predominantly used. And also there is a Tejas simulator from IIT Delhi. One professor developed that is also there. Many are there, the simulators. And similarly for the GPU side also, again, you can incorporate GPU sim is there, which is actually used for general purpose processing on GPUs. Okay. So there are, yeah, so plenty of architectural simulators are there. And if anyone is actually planning to work
currently, research are going on in IIT, right, in this multi-core process.
Which one?
Research works are going on there now in IIT.
Yeah, for example, in our group, we'll be using this Gem5 simulator for our architectural.
Up to how much multiple core we can have that?
Oh, that we can, so typically like Gem5, we can go up to, I think, the 64 cores or so on. But there are other things also. Some of the simulators from MIT and so on. You can even go for 100 plus the cores and so on. There are even works, some of the works, architectural papers, people propose for 1,000 plus cores also. Okay.
Any other queries? Okay, Madhusai have really explained, we had a detailed explanation regarding the multi-core, then GPU. We have shown the differences between multi-core and GPU. And then later on, he explained about a unified memory system on chip. And It was really a good presentation. And thank you for your talk, sir.
Yeah, thank you very much.
Thank you, Dr. Madhumutty, for that informative session on unified memory in heterogeneous computing systems, its opportunities and challenges.
Okay, thank you, sir. Thank you.
Thank you.
Hi. Hello.
Hello, sir.
Hello. How are you? Good.
Yeah, fine, sir. It's good morning for you.
Good morning.
Yeah. So I think we will start the session now.
Okay.
1 second, sir.
Okay. No problem.
We now move to the fifth keynote session of ICACC 2021. This session will be led by Professor Abram Bensleman, Professor of Computer Science, University of Avignon, France. He is also the Vice Dean of International Relations at the UFR STS. He will be giving an overview of monitoring Internet of Things or input-output virtualization network, optimization, and security. Professor completed his master's degree in CCOM at the University of Avignon. He has held various eminent positions like Chairman of Communications and Information Security of IEEE Society, International Expert at French Foreign Ministry and International Development, and also was the coordinator of Faculty of Engineering at French University in Egypt. He is a senior member of IEEE, along with being an IEEE VTS distinguished lecturer, and have several internationally acclaimed journals like IEEE and Springer to his credit. May I now invite Professor Bensleman for the keynote session. Over to you, sir.
Thank you very much for this introduction. So I will share with you my presentation here. Do you see the presentation?
Yes, sir. We can see.
Okay. So I can start?
Sure, sir. You can start the presentation.
Okay. Very good. Very good. So thank you very much for this nice introduction. I will give you a talk on this 10th International Conference on Advanced in Communication and Computing. I will talk about security aspects and also about monitoring. So you already presented my CV. So now I can go directly to the, I don't know if you. Okay, now it's fine. Okay. So in this agenda, I will talk about monitoring IoT and IOV in the first part, and I give you a theoretical approach for the optimization in monitoring. In the second part of this work, it will be likely more implementation, and I will talk about some attacks, about some threats, and about some countermeasures for in-vehicle networks attacks. And then I will conclude. Okay. So the first part is monitoring IoT and IOV. This part, I will start with some generalization, I mean. So as you can see, network monitoring solutions have become crucial nowadays because so many companies are relying on their internal networks to be productive in their line of work. So network failures and irregularities, server downtime, service or application crash can seriously threaten the livelihood of a business. What is now the solution? The solution from our side is to monitor before the problem happens. This is like a prediction before failure, before the attacks happens, etc. Okay. So how to monitor? We can identify unofficial service or servers, monitor the usage and the traffic statistics, investigate a security incident. All are the objective of monitoring. I mean, monitor is the main purpose for checking if something's wrong or something's not good happens in our network of the company or of the university or of the vehicle. Because when I am talking about IoT, I can also talk about IOV or vehicles, and I will come back on this. So we should fix the problem anytime, anywhere, okay, before the problem happens and recover immediately, okay? What are the challenges in monitoring for IoT? As you can see, monitoring IoT is important, okay? Because these IoT devices are very low power and very low small memory, and they need to preserve their energy. I mean, the battery powered in wireless device should be very, very lowly used. So the challenge, as I can see on this slide, is the topology is changing, the resources are limited, the nodes can go in sleeping mode and wake up. This is what we call the duty cycle. The density of the device are very, very big. I mean, a lot of nodes to handle. And the device are fixed or mobile. So these are all the challenge in monitoring IoT. Moreover, there is also a risk of security, as I will also explain to you in the next slides, okay? So how to do? Continuously maintaining the network's state and the availability of all the elements in real time with energy efficient and dynamic algorithm. This is our objective. We would like to minimize the resulting overhead on the network to cope with the resource limitation of IoT. This means that when we are proposing our schemes for monitoring, we should consider all this aspect. That means that when IoT application is running, we don't want to interfere on the application itself, because we would like to do the monitoring, and this monitoring, we don't want it to consume a lot of energy, we don't want it to interfere on the application, and so on. And we want to do, as I will explain, non-intrusive monitoring. Okay, so this is our objective on the monitoring. What are the schemes that have been used for monitoring? This is well known. I think all network researcher or network students know how monitoring is doing. We can distinguish two types of monitoring: active monitoring and passive monitoring. Active monitoring entails injecting test traffic onto the network and monitoring the flow of that traffic. On one hand, there are some probes that are generated, and there's generated also a specific traffic pattern. And these probes will bring data to monitor. Passive monitoring is less of an experiment and more of an observation studies. Instead of injecting artificial traffic into your network, passive monitoring entails monitoring traffic that is already on the network. So this is mainly based on some kind of overhearing the traffic that is circulating on the network. Okay, then we can also enumerate centralized, distributed, and hierarchical monitoring approach. In the centralized, there is only one entity that will collect all the information and take the decision. In distributed one, there are several centers or of authorities that will take partially the decision and then send it to another nodes, a sync or some things like this. If we are collecting information from all the nodes of the networks, and hierarchical one that's combined between centralized and distributed. Okay. Now, quickly here, I will enumerate some existing work for WSN, wireless sensor networks, IoT, and IoV. I am not talking about fixed networks. I am not talking about wireless and mobile networks. I am talking only over IoT. And here for IoT, I classified the networks layer monitoring into WSN and IoT because things are different. In one, there is it is based IP. In the other one, it is not based IP. And we can distinguish proactive or reactive monitoring in both cases. And in proactive monitoring, we can have passive monitoring or active monitoring. There are some works in IoT. The only work that I will present you in the next slide is one that have been proposed for monitoring, proactive monitoring in IoT. And also, I classified some monitoring on IUV because it is also important to monitor all the elements in the car. Because today the cars are intelligent and they have several equipment inside, a lot of, I will come back also on this, and we should also monitor the inside the car. So monitoring is important. For wireless sensor networks, there are several works that have been done, and for IoT, very few works have been, only one that I enumerate, and then we proposed some solutions. There are some theoretical solutions, and in the last part, there is practical solutions for this. And on the right of the screen, you have several methods that have been proposed. I will give to you, the reference to our published papers where you can find all these enumerated methods, okay? Now, let me go to the first, exactly the contribution, our contribution in this part of monitoring, the first contribution. I will talk about our proposed methods or models, which have been classified or enumerated into 3 methods. The first one is an heuristic. The second one is an exact solution. And the third one is a distributed scale. I will come back on this one. Okay. So let me first give you the context of our work on monitoring. We want to use a very well-known protocol and the architecture of IoT IOV. So we want to use IETF role, which is the working group that proposed a routing protocol which is called RPL. This routing protocol, before working, it proposed a tree. This tree is conceived by the border router. If you can see here, the LBR, the border router, LBR, which is low power and low Z network border router. We can have several low power border router, and we can have a lot of sensors or IoT device. And the objective here is to conceive topology for routing. This topology that have been proposed is DODAG, which is destination-oriented directed acyclic graph. So in our work, we will use a DODAG in order to conceive our protocols and our algorithm for monitoring IoT network. So RPL is based on a network which is 6LoWPAN. 6LoWPAN is low power PAN, which is based on IPv6. Okay, this is not our matter here. Here we want only to say that we conduct our research based on something that is well known. And well known is the RPL protocol, which is the routing protocol, and the DODAG, which is the destination oriented direct acyclic. So now, as input of our work is the DODAG, which is a network, but it is like a tree. Okay, so let's suppose this. The objective then is to work on this DODAG in order to do the monitoring. By the way, monitoring, we will use only the nodes of the networks to monitor the entire networks. Okay, so the first solution that have been proposed, as I explained previously, for monitoring is this one. So they propose a solution based on a DODAG in which they classify two types of nodes. There are some nodes that can do the monitoring activity and other nodes that cannot do the monitoring activity. C0 and C1 is a very low power nodes, so they cannot execute any monitoring activity tasks. And C2 will execute. So they have two DODAG. One is virtual, on which we have only the monitoring nodes, and the other one is the normal DODAG, which is dedicated to the application. And on this DODAG, we have some nodes that will do the monitoring. What is the monitoring in this situation is to collect data coming from nodes, managing this data that will be sent to the border router, which is the root of the tree, and then the decision will be taken there. For this work, there are some problems because they use overhearing promiscuous nodes, which spent a lot of energy. They don't propose any scheme to design which node will do the monitoring. They don't position this monitoring, no scheme to plus the monitoring nodes, and they don't consider any consumption of the energy in their schedule. So this is the only work that is using IoT with RPL. So in our work, we will propose a new scheme to do this, okay? Okay, so let me now go to our proposed scheme. So here, in order to do the monitoring, the placement and scheduling, we propose the first solution is a heuristic. The problem, in fact, is NP complete, NP hard, but in this first solution, we propose one heuristic. In this heuristic, we consider that we have we have a DODAG. We have one horizon, planning horizon T. And what we want to do, we want to specify a set of monitor nodes to monitor during this period, then during this period, then during this period. What is our objective? Our objective is to do not consume a lot of energy for the nodes and exhaust their battery. This is the objective, the first one. Okay, so the objective initial is to find the minimal subsets of nodes to cover to cover this DODAG while minimizing the monitoring cost. The monitor scheduling should be optimal. We start with the set of vertex. We have also our planning horizon. Now we should conceive which node will monitor during this period, which nodes will monitor during this period. This work have been published in IEEE Internet of Things Journal with my colleagues and students. I will explain it more in details. The first step, as I said, is to create multiple vertex covers. This is vertex cover problem with constraint generation. This is well-known problem, vertex cover with problem with a constraint generation. The second phase is to assign the vertex covers to the time periods. Okay, so firstly, we have a set, several sets, which are vertex covers, sets. We have the periods, and we should match between this vertex cover and this periods. The third part is another optimization, which means that we would like to do some sequencing between assigning vertex cover in order to do not exhaust a lot the nodes in monitorings. And this is well-known problem, which is known as traveling salesman's problem. I will explain more in detail this first scheme, which is heuristic. We have three phases, okay? So the first phase is to minimize and balance energy consumption of monitors. Here, okay, we create a vertex cover. It is well known in graph theory that the vertex cover cover a network of cover a graph, and it is minimal, okay? And the definition of this vertex cover is, as I explained in this slide. So each set satisfies the coverage requirement of the networks. We define VK, which is chosen if a vertex cover it is equal to 1 if it is in the vertex cover, it is equal 0 if it is not in the vertex cover. And we want to minimize this one. This minimize the sum of VK, subject to these rules: VI plus VG greater or equal to 1, and VK belong to 0 and 1. This is a sample definition of a vertex covers, and we want to create several ones, not necessarily optimal. Okay, this is the first scheme. I hope it is clear for you. The second one is more interesting because what? Because we want to assign this vertex cover. This is a set of nodes. This is a set of nodes. This is a set of nodes. I don't know if you are looking to the mouse. And we want to assign this vertex cover to some periods. We want to assign this vertex cover to some periods and so on. Okay, how to do now? We define several decision variable like this one, SIG, which means that it is equal to 1 if VCI is assigned to monitor in a period TI. For example, this vertex cover will monitor in this one and in this one, for example. So SIG, it is equal to 1 because it is monitoring in the period G, like this one. Okay. And this is a generalized assignment problem, by the way. Okay. The objectives function is, the first one is to minimize F1, which is minimize the total energy consumption. Okay. So we will use EM, which is the energy loss per each monitoring period. We will suppose that EM is constant and it is consumed for each monitoring period. For example, in this period, we will use EM. For this period, we will use EM per each monitor node. Okay. And we will multiply it by this one, this formula. Okay. Here, what we have? We have Y Ki, which is defined to indicate whether a vertex Vk is a member of vertex cover VCI. Okay. Then we have the second objective function to minimize. We want to minimize the total communication, because there is not only the energy for the monitoring, but there is also the energy for the communication between the monitoring device and the border router. This is because the monitors are ultimately transmitting the gathered information about the monitored nodes and to the root of the DODAG. So we should minimize the path, in fact, to the border router. The communication through the path to the border router. This is what we want to minimize. And how to do? We use this function. Here we have the path, I mean, the number of hops traveled from each vertex in the vertex cover I to the root of the DODAG. Important. And then we will multiply it by Y Ki. Okay. We do the sum, and then we multiply by Sig, which is the if vertex is in the period or not. And we do all this minimal. Okay. So this is the total number of hops traveled by all Vk. Now, what we want to do is to minimize and to resolve this multi-objective function, which is, as I said before, generalized assignment problem, GAP. Okay. So let me go through to this slide. I already explained what is this value, the number of times a vertex Vk has been assigned to monitor. As I said, this is a theoretical part. I mean, this is only to show to you that we can do several things important with monitorings before going to the implementation. Okay. This is the reserved battery. We should not exceed the reserved battery. This is the maximum battery allowed for the monitoring in these equations. We don't want to excel, because if you are using the devices as a monitor, you don't want to exhaust their battery only to do the monitoring. You should keep the battery for the application itself. For example, monitoring the firm, for monitoring fire, for monitoring water, etc., etc. So this is the application itself. And here we are doing only a small part of the energy for the monitoring. This is important that I want to highlight here. Okay. The third phase is this one. I mean, as you can know, in the IoT device and in IoT networks, the device can sleep and wake up, sleep and wake up. And going this transition from sleeping to wake up or from wake up to sleeping will cost energy, because this is well known in MAC layers for IoT device. What we want to do is to make economy, I mean, preserve the energy while doing this transition. So we want to make it consecutive. Instead of having, for example, here, 3 wake up, sleep, wake up, sleep, we want to use this node to monitor during only this period. Okay, and then it's enough for this node in the monitoring during all the periods. Okay, so this is what I want to highlight in this 3 phase. This 3 phase is important to preserve the energy. This is what I want to do. Okay. So we want to do minimal sequencing between the sets of monitor across the time period in Y minimized. Okay. So this is well known as traveling salesman path. We have some cities and we want to do optimization on these cities. And this is the last formulation in our proposed heuristic monitoring methods. Okay, so here you have the theory behind the third phase, which is pyramid. We want to minimize the cost. I mean, this state transition, this one, CIG, given that a node is chosen as a monitor or not. Okay. And in the figure that you have here, for example, if you take the first figure, here you have monitorings, separate monitorings. I mean, each vertex cover can monitor during this period, and then maybe they will monitor in another period, and so on. Okay, so this is separate, and this consumes a lot of energy. And here, after doing the traveling salesman path problem and resolving it, we will have a contiguous monitoring, as you can see for VC11, and the continuous monitoring for VC13, and so on. These nodes in the period 1, this is the node in period 3, this is the node in period 5, and this is the node in period. Okay, so we do a very good optimization for the state transition consumption of the energy. Okay, let me now go with the experimental studies of this first solution. Okay, as I said, we do several simulation going from 100 nodes to 200 nodes. There are a lot of instances with a different number of links in order to check the scalability of the proposed methods. Figure on the left, this depicts the effect of varying the density of the DODAG with 100. I mean, this one with 100. And the density is varying. Even if the density is varying, means that the number of nodes is varying and the number, mainly the number of link is varying. We are consuming, we are placing only a minimal number of monitors. So it is likely almost constant, the number of monitors. Why? Because we are using vertex cover, okay, for monitoring. Here it is the architecture that we use it in our simulation, like this architecture. This is a kind of DODAG going for 100 nodes and 234 links. Okay. Here we have the consumption of the battery when doing the monitoring. Figure on the top emphasizes the model capability of monitoring a dense network of 200 nodes with increasing the number of without depleting the nodes reserved battery for monitoring. So even if we increase the number of links, it is constant, the number of the percentage of residual battery. It becomes constant. In the other figures, I mean on these figures, there is a comparison between this, the different residual, I mean the maximum and the minimum. We have consumption of the battery, and we have also the average one when increasing the number of nodes. And we show that our scheme preserve also the battery even if it is increasing the number. I mean, the EM, the energy is the same for all the nodes. It is 2% of the entire battery. 2% is dedicated to monitor a period for each node. Okay. And this is a table that summarizes what I said. I mean, this table, we have 8 different DODAG. We have the percentage of nodes selected as a monitoring nodes. We have the average residual energy among monitors, and we have the percentage of reduction in the network of reduction. Okay, so you can see that here the monitor percent go from the minimal, which is 54 and 52, to 63 only, 66 only. Okay, we have not increased the number of monitor, even if we choose different instance of a DODAG. Okay, and the reduction is very interesting. Here, the reduction of the node of the state transition. This is for the phase 3, and as you can see also, the phase 3 help to decrease the consumption of the energy. Okay, but it is not consuming a lot of time, like you can see, 0.001 second. Okay, so I finished this first part about the theory. I mean, we proposed one heuristic, and then we discussed between us in this work. Now we proposed this heuristic. Why we cannot propose exact solution? Okay, and it is an extension. I mean, it is a variant of this solution. We proposed an exact solution, which is called an energy efficient multi-objective scheduling model for monitoring. And this exact solution have been proposed here: optimal proactive monitoring placement and scheduling. The first one was heuristic. This one is exact solution. Okay, for exact, in order to have a benchmark. In fact, we want to have a benchmark in order to compare what we propose, because previously in the literature, no work have been done for IoT. And this is the first. So we proposed one heuristic, then we proposed this exact solution, and currently we are working on the last one, which is distributed one. Distributed one means that we will do implementation of the protocol, and we will use Contiki Kuja in order to do the simulation and the implementation. So this comes with the end of the first part. Let me now go to the second part, which is on security for Internet of Vehicle or for connected vehicle. Firstly, we will talk about monitoring in IOV. It is important to talk about it. So the Internet of Things is englobing also Internet of Vehicles. We can use several technology in the car. For example, we are going now from the manual diagnostic to automatic. This is interesting. And I mean, we can measure the tire pressure, the temperature, braking, etc., and go to automatic diagnostic with the help of all sensors. The technology allowed current vehicles to be equipped with Wi-Fi. As you can see here, we have Wi-Fi. We have Bluetooth. We have 3G, 4G, and now we are going to 5G. It is also a kind of vulnerability for the car, because with all this technology, I mean, and access to the in-vehicles, it will be very vulnerable for security. So we should take some decision before implementing such kind of technology in the vehicles. The last part for this photography of what is used in the car is the CAN bus. CAN bus was primarily designed for reliable communication without considering cybersecurity. But I mean, it allowed to coordinate among SCU, okay, which is elements of the vehicles inside the vehicles. It will allow to communicate between these elements and all the main important modules in the car. But this CAN bus doesn't consider any cybersecurity. There is no encryption, there is no authentication, and no integrity checking, okay, for the bus CAN. This is a problem, okay? So how to monitor this dozen electrical control units is a very important problem, okay? So this is why here in red, I wrote SNMP can be a part of monitoring, because as you know, we use SNMP for monitoring in fixed networks. Why we cannot use it for in-vehicle monitoring? So here I highlight that SNMP can be used over CAN bus as framework, and it can also help us to implement and control off-board communication through cellular technology. So the vehicles are equipped with several sensors, and that collect information on speed, on acceleration, on steering angle, and air temperature. Okay, so this is the bus CAN. And we want to do the monitoring, which allow us to collect the data and then check if there is any problem on the modules themselves. Not on the data that is communicating, but on the modules themselves, okay? So two work have been proposed for doing monitoring, but they are not complete. The first one is what we call guerrilla. Guerrilla management architecture. It uses a cluster-based management mechanisms and set a mobile agent to create an autonomous management environment. To accomplish this, the nodes share the same characteristic and are aggregated into cluster managed by nomadic managers. So this is the first scheme to use SNMP. There is another one. It is not for in-car, but it is for VDTN, I mean vehicular DTN. We use SNMP as a solution which provides support to push data from VTTN nodes, I mean from cars to cars. So this man for VDTN is used to monitor the device of the cars when they are communicating between them. Okay, so this is only to monitor the communicating elements of the cars, but not inside the cars. Okay, so after talking about monitoring, now let me present to you our work on intelligent and connected vehicle security. Our work have been published recently in this book with my colleague Rajagiri, which is called Intelligent and Connected Vehicle Security. Here, we mounted several attacks in vehicles, and we really do some damage for a given part of vehicles. Okay, so I want to start this with you. Some statistics or some information about vulnerability in ICV, in intelligent and connected vehicles. Previous reports have illustrated highly practical wireless attacks on a core function of vehicles, which disengage engines and brakes, for instance, by hijacking the steering and braking unit in Ford Escape. In Toyota Prius, researchers found that while a vehicle system is getting more advanced with appealing future, the system is also becoming a vulnerable target for the attacks. In 2015, 1.4 million vehicles were subject of a recall by Chrysler because hackers could remotely take control of the Jeep digital system over the internet. In another report, a team of Chinese hackers remotely hijacked a Tesla Model S from a distance of 12 miles. In a recent study, researchers have found 14 vulnerabilities in the infotainment systems in several BMW, which is Bavarian Motor Works. Okay. Moreover, car hacking demonstrates to date have always focused in a single vehicles, but not in several vehicles. Okay. So I want to highlight this because this is important and there is still a lot of vulnerability in ICB. In this work, I will first talk about what are the attacks that we targeted in our work. Okay. What are the attacks? Due to inherent fragility of the automotive internal networks and increasing rich networking capability, the ICV are easy to suffer the threats from the network. According to the analysis that we did on ICV networking system architectures, as shown in the figure, we present three methods of attacking ICV. The first one here is in-vehicle infotainment IVE system application. We use the communication vulnerability to attack the in-vehicle infotainment system application when it interacts with the outside environment. Okay, this is the first one. The outside environment, we are working with 4G, 3G, for Wi-Fi, Bluetooth, and this is the in-vehicle, in-vehicle infotainment system. Okay. The second type of attacks is onboard, this one, onboard, okay, diagnostic, OBD, diagnostic tool, to send malicious packet to CAN bus. Here you have your CAN bus, and we send malicious packet to CAN bus through the OBD interface. The third method is to use telematics box and telematic service, TSP provider. We use this loopholes to control automobile behavior when it interacts with the data of vehicles. So we focus in our work mainly on luxury SUV Taiwanese car manufacturer. Okay. Here you have the smart key, which will communicate through with the car. You have also the KCU, which is the key control unit. Where is here? This one. Okay. You have the BCM body control module. You have the onboard diagnostic. You have the TCM transmission control module, and you have also the engine control module. Okay. So how we proceed in order to do our attacks. Okay. When the driver uses the smart key to control the door, this is the smart key, as you can see, this one is the smart key, control the door. The key chain sends the signal to the key-free control module, this one, this part on the left, on the left, this one, okay, to compare the ID number. If the ID number fits the key control unit, KCU will transmit the signal through the CAN communication system to the BCM, this one, to the BCM, which is here, okay, to the BCM, and control the door to look or unlock. Okay, so we have this checking and this verification. The intelligent remote control keyless entry system is shown in this figure. The ID code will allow to authenticate, okay, and it is a very strong way to make the control. But as we can see, communicating between the modules, KCU and BCM is vulnerable, and our attack will be on on the canvas to do the attacks. So we choose the LuxGen vehicle as an experimental vehicle because it has a lot of auxiliary systems, functions, such as cruise control system, automatic transmission system, body control system, and automatic parking system. Okay, so this is, and the implementation is on the right side of this figure, implementation of what we do. Okay, so we compare on the canvas in order to intercept what is assimilated to the BCM and what the BCM is assimilating to the car. And if we can attack here, on the CAN, this communication with the BCM, we succeed our attack. And this is what we did in this experiment. Okay, so the first experiment, as I said, is to control the dashboard. We compare with the dashboard. As you can know, the most dependent tools when driving, the instrument cluster IC display the car speed, display the engine speed, display the mileage, display several things on the dashboard. Okay. So the ICU module gains the data collected by a series of sensors, switch, and wheels, for example, sensor of the wheels in order to measure the speed and so on. And we display it. How we do this? We use these tools in order to do our attacks. In order to attack the interface of the OBD, we use these tools, which is CAN Analyst 2. This is a tool, this is a device. And we use two software, CAN Test, okay, and CAN Pro, in order to do our attack. Okay, and as you can see in the figure below, we do this attack on the canvas, of course. Okay, and what we want to do in this example is to control the panel. To control the dashboard. We want to post wrong information on the dashboard. So this figure is a screenshot of the data, the dashboard vehicle when we are using LuxGen vehicle. We found that in that dashboard, we have 161 km/h, as you can see here. The engine speed is 7,400 turns. Okay, but the engine temperature was 0, and display, the light, seat belt, and gear were in the orang. This one, this is the number of tours, and was on the orang, and impossible to achieve this if the car is in a normal driving. How can be 0 temperature, for example, given that we have 161 km/h? It is impossible. So we do our attack and we succeed to give wrong information on the dashboard. Okay, this is the first attack. We can also do some attacks in the same way on the light and on the wipers of the cars. We found that the BCM, okay, this one, BCM, is vulnerable, had no security check mechanism when it was transmitting data with other ECU, electronic control units. Okay. When the driver needs to use the lights of the wiper, the light and wiper combiner switch module, which is here column SW ECU, send the driver's intention to the BCM. It sends the driver attention to the BCM. Okay. When the BCM receives the signal of the columns from this one, okay, the information transmitted to the front control FSCU, okay, through the CAN bus, and the front control module is used to control the normal work of the light and wiper. So in this figure, we could still use the same mechanism as before to steal BCM packets from the CAN bus and to disguise our data as the real data of BCM to directly control the work of the front control modules. So we can also do some. Here, this work have been published in this conference that you can see. The last part is attacks on the localization. We did also some experiments on the localization. How we did also this. I will first, I don't know if I have still time. Yes, I have still time. I will go quickly. So to realize wrong destination attacks, attackers tampers with the final destination and get the attacker vehicle to the wrong destination or change a waypoint. This is what we want to do. So for example, in this one, instead of going to B, we want him to go to C. We trafficite, we do the attack on the navigation system, GPS and HD maps in the vehicle. We can also change the waypoints. For example, the waypoint was initially C, he should go through the C, and we make him go through to D. Okay, so this is possible also in our attacks. Okay, I will go quickly because otherwise I will run out. So what is now, let me quickly highlight what I want to show you in this table. In this table, I enumerate for you some attack schemes on GPS and on hot definition maps. Of course, there are some threats with these attacks, and we propose some countermeasures in order to overcome the attacks schemes. So I will go quickly. Third, the first column, I mean the attack scheme. We can have GPS spoofing attack. In the GPS spoofing attacks, we will have some fabrication of false GPS signals identical to the legitimate one. Okay. By the way, we are not using military GPS. We are using only civilian GPS in our experiments. Okay. There is also some GPS jamming attack. GPS jamming attack is implemented by creating a large number of radio noise on the GPS. We have also GPS replay attack, which is aimed to destroy the encryption and authentication security of GPS. We have also GPS software attack. It is mainly implemented by exploiting the vulnerability of the software itself, including the program processing for the navigation and so on. We have also Sybil attack. Sybil attack refers to an attack in which adversary exploit a malicious car to forge multiple vehicles identities and do the attacks. And we have also message falsification attack. Okay, this attack is aimed of uploading a lot of false message to update the HD map. I mean the hot definition maps. On the other columns, last one, we have the countermeasure. In the countermeasure, we can, for example, have GPS signal security. So it is vulnerable, as we can know. So we will now propose some solution in order to overcome this by increasing the and improve the signal strength of the GPS. Okay, we should optimize this GPS signal and enhance the power. But maybe add the new civilian L-band in order to do the security of the GPS signal. We can also encrypt the GPS signals via private keys. Okay. We can improve the GPS terminal resiliency of interference. We can also use the GPS ground control and monitoring systems. Here, this one. Okay. We can also, in this case, have two solutions, redundant step of key facility and encrypt telematics and communication links. We can also resolve some flaws that we have on GPS software in order to make it more resistant, while ensuring some accuracy of the data collected, some also safe update framework, and so on. Okay, let me go. In our work, we proposed this scheme. I mean, this scheme is a collect of several tasks in order to attack. Let me resume this because I am running out of time. In order to do this, these attacks, we used firstly the task one, which is remove the shell. Remove the shell. We used some IPK, Android IPK, which is called APK scan, PKID, in order to remove the shell. It is a Java cross-platform on the Android. Okay. Then we do, we bypass the signature. This is the second task. Then we analyze the decompiled code. Of course, there are a lot of subtasks, but I am going to be very fast for this. You can, I will give you the reference of this work, published already. And we have analysis of decompiled code. We have injecting malicious code. We have also repackage APK, do repackage, which is the APK tools to repackage the decompiled APK. We built malicious service, and then we conduct the attack. All these are the tasks in order to do our attacks. Okay, so our attacks was on the HD maps. So our experimental studies are used Tomcat in order to do the attack with the NAT, okay, as traversal server. We use three kinds of APK. The two first one is CLD, this one is CLD Nave CM, which is also Android APK. We use another APK, which is Navidog. We attack also this APK for Android. And the last one is by the car, which is implemented in the Luxgen vehicle. So quickly, in this first figure, okay, the result of attacking CLD Nave, CLD Nave CM, okay, display a normal route on the left and attacked route on the right. We can see that. Dingxian dormitory, which was scheduled as a waypoint, was changed in the second one. Okay, so we go through another waypoint, and the destination also was changed. The destination was changed. Okay, before the driver starts, we changed the maps inside the car, and he changed also the way. Okay, the second one is the attack on Navidog. The same, we can change with Navidog, okay, the route, okay. We change the waypoint, and we change also the destination. Okay, so this is likely some kind of technical part, because we used a lot of materials, I mean a lot of APK, in order to check the resistance of all the APK that can be used to attack this HD maps. Okay, and the last one before I finish is when we used Baidu Car Life. Baidu Car Life, it is one APK that is used in Luxgen car, okay. As I explained before, we did a lot of experiment on LXJU attacks on LXJU car. This figure show pre-attack route and post-attack route on the IVI system screen. Okay, so we change the displaying information and also we change the path and the route. Okay, this work on the navigation attacks for the cars have been published in this IEEE Wireless Communication magazine, and I would like to thank my colleagues because I worked with them when I visited them in 2019 in order to do all this experiment with them on the car. Okay, so now I come to the end of my talk. I proposed several solutions for monitoring IoT. It is still matter to consider monitoring in IUV, and mainly in vehicles monitoring is still important, mainly if we don't want to use CAN bus, but it is the well used tools in the cars. Maybe you can consider Bluetooth, but it is not very secure, it is not very powerful. Maybe we can use UWB. So this is the in vehicles. We have also to consider security when we are using 5G. It is still open, and mobility and management is also a big problem for this kind of technology that is introduced in car systems. Thank you for having listened to me. If you have any question, I am happy to answer.
Does the audience have any questions? Anybody? Okay, thank you, sir. Session.
Thank you, Professor Ibrahim Bensleman, for that informative session on monitoring Internet of Things, input-output visualization, optimization, and security.
Thank you. So wish you a good continuation. Bye-bye.
Yes, thank you, sir.
We have now come to the end of today's keynote sessions. We will now start with the afternoon technical sessions, which will be conducted in two venues parallelly, namely Multimedia Hall and Senior Lab. The session to be held in this hall will be chaired by Dr. Binsu Kovu, mainly related to image processing domain. The parallel session in the adjacent hall will be chaired by Dr. Deepthi Das Krishna, that will mainly relate to smart communication domain. Help desk team seated outside this hall will give needed assistance for all your queries.
Paper ID number 112 will present now. Please note that your time is 10 minutes.
So good afternoon, everybody. I'm Anjana Unnikrishnan. I'm the co-author of the paper Identification of Drowning Victims in Freshwater Bodies using Drift Prediction and Image Processing based on Deep Learning. On behalf of all my co-authors, Anusha PR, Roshni Eti, Anjum Minni, and Mr. Anurag CK, who is our guide, we present before you our project. So this was actually our final year project in BTech. So this is today's outline. Last year, one of my co-author Roshni's neighbor went to fishing in near BOT bridge in Ernakulam. So he jumped into the river in search of his lost paddle, and unfortunately he got drowned, and he was found after about 4 hours of rescue process. Unfortunately, he lost his life. So this incident has led us to think about a system that could improve the search and rescue process in underwater conditions. The goal of our project is to address this deficiency to bring out an efficient system that can be used in low-tech freshwater systems like dams, lakes, etc., and to detect these drowning people. So we mainly used this analyzing the water. By analyzing the water current, we predict the drift of the person. Then we use the multiple sensor data, data from multiple sensors, such that we could capacitate this human detection as fast as possible, so as to ease this rescue process. And the human detection is done using YOLO V3 algorithm, which will be faster enough for human detection. Then mainly there are conventional and technological detection methods existing. So the first one is conventional, in which manual search is the most common solution that exists today. But it takes a lot of time, as I mentioned earlier about the incident, and as well as many innocent lives are lost due to this manual search. And another way of conventional way is fishing, using a fishing net, but that is never a proper solution to this problem. Then the technological methods that we use, or the existing ones, are using sensors like ultrasonic sensor or PIR sensors. Then also some cameras, underwater cameras can be used for this purpose. But any of these technologies is not a proper solution to this problem, and are mostly inaccessible to people around the world. For the development of our project, we have reviewed some of the existing works. The first one was of Mr. Carniel S. et al. In his paper tracking the drift of a human body in coastal ocean using numerical prediction models of oceanic, atmospheric, and wave condition. So in the system, he uses a Lagrangian model for the prediction of humans in oceanic regions. And also the main disadvantage is that it can only be used in oceanic systems. So in low-tech freshwater systems or in local areas, it is not at all useful. And the second system we reviewed is of Mr. Bakar S.A.A. et al. He implemented ultrasonic sensor to detect the objects in underwater regions. Then the third one is a monocular vision-based underwater object detection system, which was proposed by Mr. Chen Izzard et al. After reviewing these papers, we understood that using a single method to identify these humans in underwater is less efficient, whereas if we combine the visual as well as these ultrasonic sensor data, that improves the underwater object or underwater human detection. So we came into a conclusion like that. And so our proposed system is actually a portable device which can be attached to boats or drones. Once the device is deployed in the water surface, on analyzing the drift distance of this human, after analyzing this drift distance, the ultrasonic sensor is activated. Then if an object is in front of this ultrasonic sensor, the camera will be activated. Then this camera is actually doing a real-time detection using YOLO V3 algorithm, so as to detect the humans faster. So this is the explanation of the same, what I have explained. Then So for the implementation of our project, we have proposed two algorithms. The first one is to retrieve water current and distance of the object from the device. So this is the algorithm. Then the two functions we have used to get the water current and the distance. Then the second algorithm is to calculate the drift distance using a mathematical model that was proposed by Mr. John Ellis in his paper Time Required for a Drowning Victim to Reach Bottom, and the real-time object detection using YOLO V3 algorithm. So this is the second algorithm. Then the overall working can be seen here. So in this, let me explain the overall working of the system. So here, the water flow sensor and the ultrasonic sensor are connected to a Jetson Nano, which is an edge computing device. So through an Arduino board. So when a controller initiates a search, the Jetson Nano requests the Arduino for the drift distance for the water current, and this using this water current, we predicts the drift distance of the victim underwater and acknowledge it back to the controller. So this Jetson Nano then activates the ultrasonic sensor and starts scanning using it. So the speciality of ultrasonic sensor is that we can detect an object that is we can detect an object in a wide range of area, but when the object is so close to it, it will be difficult for that ultrasonic sensor to identify the object. So that's where the importance of camera comes in. So the camera can detect an object that is very close to it. So when we implement the real-time detection using this YOLO V3 algorithm, the camera will be able to identify the objects that are nearby to it, whereas the ultrasonic sensor will be able to identify the objects in a wide range of area. So this will be really useful if we implement this. Then actually we have implemented the system using a DOL instead of human. We prepared a data set with the pictures of DOL in underwater, and we trained the data set. Then we implemented this using this DOL, and so the results that we obtained is, so for the drift prediction model, the accuracy of the drift prediction model was evaluated by deploying it in various water currents in Muattivura River. So the one of the example is given here. So a dole of weight, a dole of weight 3.85 kilogram and height 12.6 centimeter was dropped into the Muattivura River, where the water current was 0.1 meter per second, and it drifted away for a distance of 0.2 meter. So after we have implemented our system, the system that our system predicted an average or approximate drifted distance of 0.15 meter. So that is how we evaluated the drift prediction model. So this is the chart which shows the mean average precision and loss of the those incurred during the training of our data set using this DOL. Here the x-axis represents the iteration and the y-axis represents the MAP as well as the loss incurred. Then this is the object detection. The YOLO V3 object detection model has achieved an accuracy of 82.10%, and the detection time was 48 seconds. That is actually, it took, the drift distance was predicted in 3 seconds, and the object detection model detected the human in 48 seconds.
Please note that you have 1 more minute.
So the results of DOL detection in two different environments. The one in Muattivura River was about 98% accuracy, and the other was a turbid canal nearby that, which has an accuracy of 83%. So basically, our proposed system has an accuracy of 82.10%, and the speed of detection is 48 seconds. So this is an improvement to the existing systems to detect humans underwater, and the portability of our project will be very useful for easy user access. Then, so we plan to extend our application to tourist spots, so where the tourists may be unaware of the river environments. So that could be helpful for them as well. Also, we plan to extend our database data set such that we could identify a wide range of objects in underwater conditions, as well as it will be useful for criminal investigation purposes. So also we plan to add an auto-inflatable PFD, which will be useful for victims to survive until the rescue team arrives. And that's about, and these are some of the few references that we refer. And that's it. Thank you.
Okay, Anjana, you presented a good paper. I just want to ask, in the slide number 40, you have included a number 13.3511. How do you get it? Slide number 40.
Yes, ma'am. That is actually when we calculate the distance using ultrasonic sensor in air and water, that will be different. So in water, it travels faster. So after converting that value into for underwater conditions, we need to use this value to identify the or calculate the distance using ultrasonic sensor. Yeah.
Oceanic spaces in it. How did you find out in the first literature survey?
So actually his paper proposed that it can only be used in oceanic region. So the parameters that he used to identify this is this wave conditions, as well as the winds where the parameters he used to identify. So in a lake or a dam like area, there will not be any wind, or as much as that of an ocean, there will not be a wind. So we will not be able to use in such conditions.
Have you checked your experiment how far an object?
5 meter. We used an ultrasonic sensor that can detect up to 5 meter. So if we increase we use an efficient ultrasonic sensor, we could increase the range as well.
Camera?
Camera actually detected a range of 8 meters. Okay. Like after this ultrasonic sensor identifies an object in front of it, the camera will be activated.
Can you use an ultrasonic sensor, or do you use some hydrophones or something?
Excuse me?
This ultrasonic sensor is usually used for measuring the distance of the obstacle.
Distance of this object. So if you actually
in air, right? Not in water.
Not in
water.
Yeah, there are underwater ultrasonic
right?
sensors. Yeah, we experimented it using an underwater ultrasonic sensor.
Okay, so how do you decide like where to focus? Because once the event has happened, drowning has happened, it must happen sometime before you start the search and rescue, right?
Yeah, we will have an idea that he might have fallen here. So we will deploy the system there. From there, the drift distance will be calculated based on the weight and height of this person. Like an estimated height and weight of this person, we will identify this drift. So we will identify that he might have drifted away for 2 meters or 4 meters. So that area will be concentrated for the search. So if it is not found, we could either attach this device to a boat or a drone-like device. So we are possible to cover a large area in small amount of time. That is our main purpose, because manual search, like searching manually, will take a lot of amount of time. So reducing that is our main objective.
But is it practically possible for the doll? It's fine, but actually, like if the body drifts off quite some distance, then will this ultrasonic sensor with a range of like 5
like
meters,
the device will be moving and searching. It will not be standing. It will not be standing still in this water. It will be moving. That is why like we could attach it to a boat or drone. So like when it is moving, if one area is covered, then move to next area. Then we could cover that area as well.
Okay, thank you.
Thank you, sir.
Hi team, very happy to see your work. And application point of view, it's a good work. But when it comes to research, I have a query. Like, you have client, like you have improved the accuracy of the method, right? In the conclusion, you have improved the object detection accuracy of the current methods, right?
Yeah.
So how you have altered the model, or do you have any modifications on the YOLO V3
Like
to
the
improve the accuracy?
like the versions of YOLO are increasing, so it is reached until YOLO 5, I think. So if we improve the this algorithm as well, the object detection can be made faster. Even from this 48 seconds, it may decrease to even 20 seconds or 30 seconds. In 30 seconds time, we may detect this object. So that is a great improvement while in this life rescue applications.
Yeah, that's actually the improvement of YOLO, right? According to your system, do you have any modifications done to improve the accuracy of the entire system?
Accuracy. So, as suggested in the future work, we will be adding a PFD or such systems. That PFD is actually a personal flotation device which can be attached to this device. So, when a victim is identified, if he is alive, he could survive with this PFD until this rescue team arrives. So
Okay.
that will be that will be good to save a person from death actually.
Okay, one more client. You have claimed that the YOLO V3 is faster enough to detect the process, right?
So when we proposed this idea, we were when we worked on this, we came to a conclusion that YOLO V3 will be best suited for this. So after that, the YOLO 5, then YOLO 4 and YOLO 5 versions came. So we could improve that, like change to this YOLO 5 and all.
And like the frames, are you using all the frames captured by the camera for the detection purpose?
It is actually using real-time detection now. So
No,
whatever comes in front of it, the algorithm is running live in the background such that whenever an object comes in front of it, that will be focused and search whether it is a human or not.
No, I'm asking like, what is the frame rate of the camera you have used?
Excuse me?
Frame rate of the camera you have used?
45 FPS, I think so.
45. So if you are applying YOLO V3 to 45 images, it lag, right?
Yeah.
So the system may be delayed. The purpose of the entire system may be collapsed.
Yeah. Let me think of
Yeah. There should be some algorithm to select the number of frames.
Yeah.
Okay, then you can improve the method.
Yeah. Thank you for that.
The next paper will be paper ID number 113, which will present the topic real-time vision-based Bangla Sign Language detection using convolutional neural network. This will be presented in the online mode.
Can I start presenting my work?
ഇനി എത്ര ഓൺലൈൻ ഉണ്ട്? ഓൺലൈനിൽ എത്ര ഓൺലൈൻ ഉണ്ട്?
Paper ID number 113 will present now. Please note that your time is 10 minutes.
Thank you. Good afternoon, everyone. Title of our main step is real-time vision-based Bangla sign language detection using convolution language. Authored by
Sir, we cannot hear you.
Can you hear me now?
You're still not audible.
Can you hear me now?
You're still not audible to us.
Hello.
Yes, sir, you're audible.
Okay.
Please note, paper ID number 113 will be presenting now. Please note that your time limit is 10 minutes.
Good afternoon, everyone. The title of our manuscript is Real-Time Vision-Based Bangla Sign Language Detection Using Convolutional Neural Network, authored by Riyad Rafiq, S.M. Azizul Hakim, and Tahsina Tabassum, which is presented by myself, S.M. Azizul Hakim. Sign language is a way of communication for hearing and speech impaired individual, which is usually performed through various handshakes and motions. Although it is the only way to communicate with these hearing and speech impaired individuals, most of the general population don't know this language. So there is a real communication gap between these two groups of people. We haven't found many effective works on this digital sign language detection, especially in Bangla. There are some data-driven deep learning approaches, but mostly for alphabets and not in real time. So our goal is to build a sign language detection system which can pave their way to bridge this communication gap between these two people, groups of people. Our system recognizes 10 Bangla sign language words in real time. We have collected a total of 1,500 images from 10 healthy subjects for 10 words. Images were then resized to a smaller and square shape and converted to grayscale for reducing the computational complexity. All images went to some augmentation techniques like rotation with shift, height shift, shear, and zooming. This augmentation technique helped us to build a robust model for real-time application with a relatively smaller amount of data. In figure 1, you can see the example of a sample data set which are converted to grayscale. So in figure 2, you can see the block diagram of our proposed model. In the training phase, we trained our CNN model with the processed data set. And in the detection phase, we received the input from a live webcam, and the region of interest, which is the handshake, is extracted. Then through some pre-processing, this handshake is then fed into the CNN model for prediction, and the result is shown in the screen real time. Our proposed model is a novel 7-layer sequential CNN model, which consisted of 4 CNN layers to full connection layers and a softmax layer. So this model is basically a lightweight, a smaller version of GGG16 model. When considering the real-time application, we actually wanted a model which is faster, smaller, and also can perform well. So after experimenting with a number of convolutional blocks, we found that this structure is much more efficient for smaller number of data sets, smaller data sets. So at the implementation stage, our system takes input from a live webcam stream, and then we actually detect the region of interest, which is the hand shape from using the TensorFlow object detection API for each frame. And then this hand shape is then resized and converted to grayscale, similar to the dataset reprocessing steps, and then fed into the CNN model for prediction. Here you can see in figure 4 the real-time prediction results. So we have experimented with different image sizes, and larger images actually gets better accuracy, but keeping in mind in the computational complexity, we decided to go with the 64 by 64 images. We also experimented with the train split and found that 70:30% split is the optimal. So with these settings, we finally trained our model. And after that, each gesture is predicted with 50 samples, and the result is converted into a confusion matrix. Here we can see the average precision, recall, and F1 score is around 97%, and accuracy is 97%. So our proposed CNN model clearly outperforms the existing similar models. So our work is focused on a small subset of automatic Bangla sign language recognition, and the intent of this work is basically to facilitate a conversation between these here impaired people and the average population. In an Intel 4th generation Core i3 CPU, our system gets average response time of 120 milliseconds, which is a lot faster. Possible extension of this work can be done by gathering a large number of data, keeping in mind the various demographics like age, gender, and race, and training this data with existing pre-trained models, which can be make a better and a more robust model. But obviously, there is a drawback to this system. If the number of words gets much bigger, then we will have to build a much larger model, which will be definitely be slower, so may not be efficient for real-time applications. However, this baseline is a baseline for the future enhancement of this in this domain. Thank you, everyone. I'd be happy to answer any question regarding our work.
Thank you, Assessor Hakim. I just want to ask, what is the ground truth? How did you decide that your system is accurate like that? What did you
we have, after training the model, we have run our entire data set, predicted all the images. So then
that hand gestures, which position you are considering that particular word? Is there any angle or anything like that, or simply keeping the?
No, we can just keep the hand gesture in front of the camera webcam, and it actually takes the reason of interest, the handshake, and then get processed, and we can get an output.
And how did you decide how many convolution layer, how many max pool, and all?
We have actually started from the VGG16 and tried to experiment with different layers and different settings, and actually found out that this is the, we have trained several models and found out that this is actually the better model in terms of accuracy.
Okay.
Hello, I have a few questions. This is for static hand gesture recognition, right?
Yes.
And one more thing, what sort of pre-processing did you use for the cropped out image? Before
sorry.
What sort of pre-processing did you do to the cropped out region before you put input it into the CNN?
It just resized into 64 into 64 shape and then grayscale, converted to grayscale. These two, just.
And how do you crop out the region of interest? What sort of algorithm did you use?
Okay, we use the TensorFlow object detection API. Actually, we got the prop region from this. So it was the default open source API.
Yeah, but it must be using some algorithm, YOLO or something of that sort, right? Or fast
Yes.
Which one is the one which is being used?
Yes, TensorFlow object detection algorithm actually uses EULA v3 probably behind the hood actually to detect the region.
So once you detect it, you resize it in the 64 by 64, right?
Yes, yes.
But you didn't do any pre-processing, image enhancement and things of that sort before you fed it to the CNN?
No, we didn't do that. We just resized it and converted it to grayscale.
Okay, thank you.
Thank you.
Hi. Can you show me the 10 signs you have used for the detection used in your data set?
Excuse me, can you say that again?
Can you show me the 10 different classes of hand gestures you have used in your work?
Okay, I actually don't have in my slide 10 different. There are the 5 of them.
Yeah, I will ask you one thing. In the third and fourth one, okay.
Okay, yes.
So if you done an augmentation like rotation, okay, if you slightly rotate of 45 degree,
yes,
the third class become the fourth one, right?
Okay, yes, we actually kind of did a 10 degree rotation probably. It was not too much.
Okay. And also, the one of the major drawback of CNN is like it will check on the sub parts of the images, right?
Yes.
So for most of the hand gestures, all the subparts will be there. So there is a chance for the misclassification, right? How did you handle that? Because in the third one and the fourth one, the subparts like the thumb, the fingers, the palm, everything is there, right? So it may get confused, the CNN may get confused, like both will be same.
Yes, actually, we are working on that, and we will be extending our work, and we have this in mind to handling these misclassifications.
Okay, then how did you achieve this accuracy of 97% if misclassifications are there?
Yeah, there are some misclassification, but not that much. Actually,
did you include that confusion matrix?
No, actually, I didn't.
Okay, fine. Thank you.
Thank you, sir. We'll begin the next presentation. The next paper to be presented is paper ID number 125 on the topic object classification in underwater sonar images using transfer learning based ensemble model.
It's asking for an account. It's asking for the account.
Login ചെയ്യാൻ sir.
Paper ID number 125 will be presenting now. Please note that your time is 10 minutes.
Good afternoon. I'm Divya Bharati here, and I'm here to present my paper titled Object Classification in Underwater Sonar Images using Transfer Learning Based Ensemble Model. And my co-authors are Dr. S. Shailesh and Dr. M.V. Judy from the Department of Computer Application, CUSAT. And this paper is a part of a funded project called Digital Pumbuhar. And actually, the idea of this project assigned for me was to find the artifacts and cultural heritage from the seabed which is under the ocean, which has been before 3,000 years, and we are trying to find artifacts from there. And this is an initial stage where we try to find the ships and airplanes from the data set we got from the publics. And our basically this naval and military research has a significant attention on the targets which are present in the underwater seabed area, and these are crucial because of the data collection, because there are various types of collections like optical data collections and sonar data collections. But in optical data collection, the stability of ocean is very much needed, and whereas in sonar devices there is no issues in transparency issues, and we can collect from the surface of it. And we are using the sonar data here, and we are trying to do automatic object detection, and we can explore the complex ecosystem and the ocean bed. And we are presenting here an ensemble approach using transfer learning to detect the objects, and our classification has an accuracy of 90%. And introduction is like, so what are the complex characteristics of ocean bed might be?
it can be canyons, sea mounts, and thermal vents and methane seeps are the major characteristics in the seabed. Along with that, the climate changes and the collection expensive collection and time consuming for the scanning of it. So there are two types of scanning in sonars. So one is active scanning and one is passive scanning. So this side scan sonar comes under active scanning, where the receiver and transducer are set to a hull, and we collect the data from there. And so when we had started with the project, we came across this issue of sonar data available publicly, and we found, fortunately, we found one resource from the public repository, and we are using that. And about transfer learning, it's a pre-trained model. We are using the weights or the knowledge gained from the ImageNet trained weights. And for next is ensemble. A method is used for combining the machine learning methods rather than using it individually. So this is a picture where how the collection is done in the figure 1. And from the study, we found out unless it is a private data set, everyone is coming across this data limitation issues and the performance with the individual classifiers. So we are going to address with the improvising the generalization with transfer learning. With the transfer learning, we are going to improve the generalization, and the model we used is ResNet 50. And for the instead of using individual ML classifiers, we are trying to do with ensemble learning to improve the classification accuracy also. So so this figure shows the sample images from the data set. So the first one in the top is a shipwreck, and this below one is an airplane wreck, and the data set named is seabed object ship and airplane data set. And as I said earlier, it's side scan sonar data. There are various sonar available, like synthetic aperture sonar and forward looking sonar, but we got this from GitHub. And we have used around only 127 objects, whereas for 62 was airplanes and 65 was ships. And the proposed model is a two-step process. One is a feature extraction process, and another one is a classification process. So majorly the idea is to discriminate between the shipwreck and the planes. We extract the significant features from the ResNet 50 after training the our available data with that. And characteristics about this is an architecture of the ResNet 50, and it has around 48 convolution layers with 2 pooling layers. And then the final layer, first we train the data with the ResNet, and the feature vectors are from the last layer transferred to the classification module. So in this figure, we can see the pipeline of our model. And we have in the module after transfer learning in the ensemble module, we have used logistic regression, random forest, and Bayes and SVM as our possible combinations, which work best for our data especially. And with the help of soft voting as our voting classifier, we achieved a good classification with less error rate. And this is a comparison of individual classifiers with our ensemble model, and we achieved accuracy around 90% for our module. And the results represents the true positive, and rate is higher. And from the ROC curve, we can find that the performance of the model is good comparatively with the individual classifiers. So from that, we found out this actually tailored especially for the sonar image data set. And from the evaluation metrics, we found out it's a better solution for sonar classification. And this can also be customizable for other data sets also. And so further, we can increase the efficiency if we get enough data. Thank you.
Okay, thank you, Devi.
Thank you.
Your work is based on the GitHub data, isn't it? GitHub data. You take the data from the GitHub.
Yes.
And what are the reason of the misclassification? You have found that 3 data is not classifying properly, isn't it? What can be the reason you have?
Since it is a rec, the parts of the image object are hidden. So only the mild or very less, and that cases only it has misclassified it. Otherwise, if the outline or the boundaries are better, it is classifying.
You have extracted the data from the ResNet and you take that features and just given to the different machine learning model. That is what you have done, isn't it? What's your contribution?
So this sonar image is this is under a project. So we are working for the project. So as a project we will get more objects also. So this is an initial step where we are trying to building a model for the project. So we found out that better than individual ensemble is better than an individual model than.
Ensemble means you have included everything.
Yes, ma'am. Thank you.
So how do you obtain the sonar image using active sonar, right?
Sir?
How do you obtain the sonar image? For that you have to use active sonar, right?
Which sonar, sir?
Active.
Yes, active sonar.
So you didn't do it, you got the data from GitHub.
Yeah.
Out of the 127 images, how many of them were used for training and testing? 70%, 30%?
80-20.
80-20.
Yeah.
Now, how many features were there? The features are extracted from the last convolutional layer of the ResNet, right? The features.
Features.
How many features were there? See, that is used for the logistic regression, random forest, Naive and SVM. So what you usually do is you flatten the.
Yeah, flatten.
How many features were there? The flattened features.
Right now,
See, I have another question. You could also use the traditional feed-forward neural network, multi-layer perceptron for classification, right? After flattening. You didn't do that?
Which one, sir?
After the flattening, you could have used a traditional fully connected neural network.
We did not do.
Why didn't you do that? You could have done that.
The accuracy was similar to the other classifiers like SVM, like this. We need more accuracy. So
I would guess that, like, if you use a fully connected neural network, 1 or 2 layers, hidden layers, then that will give good performance. One more thing, in figure 5, here you say feature extraction model summary, and you have only 2 classes, right? Ship or
airplane.
Airplane. So in this, you are showing like several dense layers, and the finer dense layer has only 1 node. Figure 5 in your paper.
Yes, sir.
What exactly is that? That 1 node. If you are using these dense layers come only after the convolutional layers, right?
Yes.
So why did you use those dense layers? What did you use it for? Finally, accuracy obtained from the models. There you are not showing these classification based on the dense.
That is for transfer learning. When it is happening in transfer learning, that are the parameters and dense layers.
Don't know. There's some issue of clarity over here. Figure 5. What is it? Feature extraction model summary. That's what you are saying. And you are saying they are all dense layers.
Yes, sir.
Okay. How do you obtain the ROC?
True positive against false positive from the testing data.
You didn't have to explicitly do it. It came as part of the.
Explicitly we did, sir.
Okay. Okay, that's all. Thank you.
Thank you.
You mentioned that the database is downloaded from GitHub.
Yes, sir.
Actually, you are doing this project, I think in the current first slide, I saw that it is from Cochin University. So you may contact with the NPL, they will provide the sonar images for better results.
Sir, we contacted, but we could not get it.
Okay.
There
may be the principal investigator can contact them, they may give.
Yes,
Because
sir,
I was an
we tried
experience with
our
sonar
best.
image. That's
Yeah,
why
we
I'm-
tried at NIOT Chennai, NPOL here also, but we could not get. Actually, there are a lot of procedures are there. So
Yes, that I agreed. Okay, that I agreed.
So, and we thought there was because of COVID issues, there was a deal. Actually, we thought we will get directly from our project. And what happened was due to COVID, the ship can't go to this ocean and the delayed was happening.
No, I'm saying that there are a lot of sonar images are already available in NPL. You may get it. That's one suggestion.
Yes, yes.
Okay. Whether this downloaded images, downloaded sonar data is in the form of image or in any other form?
Image form.
In the form of image.
Yes.
That means you are simply doing the JPEG.
Yes.
Whether in the form of JPEG.
Yes, sir.
So the better to model your network is that you can similarly train and test with another databases also. Then you can say that this will work for this database also. You can download another databases because this is actually downloaded in the form of JPEG. There are a lot of databases are available in the form of JPEG in already available.
Yes.
In Kaggle or something like that. So you can simply download the database and you can test your networks. Okay. And one more, how many images that you used in your work? Can you show that confusion matrix?
That is for testing data.
How many images that you used for training and testing?
80-20 proportion.
No, I'm asking that number. Because here actually the number of images used previous slide. I mean the
last one.
Yes, this one. You can add 33, 36, 39 images.
Yes, sir.
For testing.
Yes, sir.
How many images for training? Approximately 100 images.
Yes.
The number of images used for training and similarly for testing is very less. Because you are using the deep neural networks, ResNet. So if you are saying the accuracy and similarly the confusion matrix or whatever it is, ROC curves, definitely the number of images should be more.
We tried acquiring other sonar images.
No, I am saying that you can try with another images also. This is my suggestion.
Oh, sure. We'll try this definitely, sir.
Okay.
Thank you, sir.
Which platform that you used?
TensorFlow.
TensorFlow.
A grayscale.
Only ship and
airplane rig.
Whether any noise removal or any such type of algorithms used?
Speckle noise and basic noise removal we did.
What are the noise removal?
Speckle noise we removed and the blurring that we did. Blurring was removed. And we got data, mostly it's clear only. We just cropped it and did the...
You manually crop?
No.
The RO...
We resized it, just we resized it.
Resized.
Resized. Sir, we just removed
to make it clearer, we removed the histogram equalization and those basic things only.
So median filters.
Median filters we did not, histogram equalization we did just to equalize the filter lighting effects so that the boundaries are more clearer.
Okay.
The next paper to be presented is paper ID number 87 on the topic various approaches in plant species identification and plant disease detection using digital images of leaves. Paper ID number 87 is presenting now. Please note that your time limit is 10 minutes.
Good afternoon, all. My name is Annie, and co-author is Dr. Shirley KK. Today, I'm going to present about various approaches in plant species identification and plant disease detection using digital images of leaves. And here's the outline: introduction, methodologies, related works, comparative study, applications, and conclusion and reference. Introduction. As we all know that plants and trees are an inevitable part of our life. They contribute to biodiversity, provide clean and fresh air, prevent soil erosion, and many more uses. Acquiring this knowledge is very important, and identification of species is very complex and consuming for the novices. But many species are endangered due to the human encroachment and due to diseases affecting them. And so the timely and accurate recognition of diseases is of utmost importance. Recent developments in the AI and smartphone technologies and digital image processing has enabled this automation of identification and disease detection process using the digital images of leaves. And here we discuss two approaches. One is the conventional method using the machine learning techniques, and the other is using the deep learning technologies. The conventional machine learning method. Here's the general architecture: image acquisition, image preprocessing, image segmentation, feature extraction, classification model, and the model prediction. In the case of leaf identification, the image acquisition can be get from the standard dataset like Swedish datasets, Folio, Flavia, LeafSnap, and we can also make use of manually created datasets. And in the image preprocessing, we can reduce the noise actually by rotating, resizing, or applying filters. And image segmentation, we can make use of various thresholding techniques. In the feature extraction, in the case of leaves, we can make use of color, texture, and the shape, boundary, and venation features. And the classifiers, there are many classifiers available, and we can make use of like SVM, KNN, MLP, etc. We can even use multi-learners also. And the prediction, we will in that case, plant species name will be predicted. And here is the testing done on the Kaggle leaf classification data sets. It's a feature data sets, and I have employed 7 classifiers. Among them, the 3 classifiers outperformed are KNN, Logistic, and MLP. And also have applied that feature dimensionality reduction technique PCA. And this also proves that the PCA has improved or maintained the performance metrics compared to the original dimensionality. And here is a similar phases are there in the disease detection also in the conventional approach. Only slight variation we can find that the standard data set mainly used are plant doc and plant village. Plant village has more real images. And there are other data sets also specific to the crops. And the difference in image segmentation is here we need to do the dual segmentation and the histogram equalization for contrast for improving the quality. And the feature extraction, mainly color features and texture features, can be used for feature extraction in the case of disease detection. And while the prediction for the classification, like unsupervised learning algorithm, can also come into play, like k-means clustering and all. Class predictions, we can either predict whether the leaf contained diseases or whether we can predict the species, what type of disease it is, or whether we can predict the severity of the disease. And next is approach using the deep learning techniques. As we all know that deep learning techniques will employ so many layers between the input and output layer compared to the simple neural network. And there are different models, ANN, CNN, RNN, autoencoders. So here we focus on the CNN model. And there are two approaches, is training from scratch and transfer learning. In the training from scratch, we customize the model. We decide how many numbers of layers should be there, or how many number of neurons should be there in each layer. But in the case of transfer learning, we are taking the data from a pre-trained model. Pre-trained models, which are usually trained on the big data sets like ImageNet and all. Examples are VGG 16, 19, ResNet, Inception, etc. And here is a testing done on various pre-trained model in the plant village data sets for an epoch of 15. And it's from the graph, it's noted that VGG 16 performs well, and the validation accuracy is more in the case of compared to the other models. And similarly, the validation loss also minimum for the VGG 16 model. And next approach is SIMS network. So as we know, the deep learning is data hungry, and suppose if you are having a less number of images for training, it's a better option is to use the SIMS network. It's none other than a dual CNN or MLP network. They share the common configuration of weights or parameters. Here we input an image pair, and they will be image pair, and the output will be from the output. It will be noted whether each pair belong to same species or different species. So though it is computationally expensive, it performs well, and it is having a good generalization capabilities. And here are different. Whenever the two images are given, their features are extracted using this convolution model, and from that we will calculate the distance. It can be L1 norm, L2 norm, inner product, or cosine similarity. Here's the general architecture of the same. And with the SIMS model, also have done some testing with the medicinal leaf data set available in the internet. And from this, I have used VGG 16, 19, Inception V3, and SM means a simple customized model. SM, it contains only two convolutional layers followed by average pooling and a tannage activation. Here, the accuracy is more for the SM model. And similarly, the validation loss also was minimum for this symbol model. And the epoch taken was number 25. Related works. In the first paper, this reference 25, they make use of the supervised learning algorithms, and they make use of 14 classifiers and accuracy range from 84.6 to 99%. And they found an optimal combination of features such as geometry, color, Wernicke moments, and totaling to 38 features. They took the help of Picard tool also. And next paper, they have conducted, as Anupa Pierli et al., they have conducted experiment on both conventional method and the deep learning approaches. They got a good accuracy in the deep learning approach, and they have with VGG 16 and VGG 19 model, and with LR logistic regression classifiers. And the next paper, it is based on, they have conducted, it's for the disease detection, and they have conducted 60 experimental configurations, and based on which type of architecture they have used, whether it is a training from AlexNet or GoogleNet, whether it is transfer learning or training from scratch, whether the image data set is color, grayscale, or segmented. And the choice of the training data set also differ in each cases, 80:20, 60:40, etc. They got a good results in the GoogleNet transfer learning color image 80:20 ratio. And the next paper, it is they are actually designing a training from scratch model. It's a multi-scale fusion convolutional neural network. And here an image is downsampled into low resolution images, and their features are extracted at different levels and concatenated. And they got a good accuracy in the MalIQ dataset D1. And they have also done the cross dataset evaluation also. They train in MalIQ and tested in the LibSnap. The next paper is plant disease classification using deep CIMUS. Here also they have compared with the transfer learning as well as in the CIMUS network, and they got a better performance using the CIMUS network. This is the architecture of the same. Next paper, it is for the plant disease detection. Here they have started their research in 2018 and developed a plant disease detection platform. And they have actually done a transfer learning from their own previous model. And they got a good results with single layer perceptron it was trained for 100 epochs with the Adam optimizer. 95.71 accuracy was the achievement. And next is the CIMUS network. They have made use of the CIMUS network for the plant identification process. And here they have used the best model. They got the performance best in the inception before structure, and they have made use of KNN classify for classifying. And they use very less number of images. Like their test training images, it ranges from 5 to 20. And they got a result in the 20th that they got a good result in the inception before structure.
Please note you have 1 more minute. 1 more minute. 1 more minute. You have 1 more minute. You have 1 more minute.
Okay. Next paper, next paper they have used of convolution layer and deconvolution layer in order to know, and they found that the different orders of Venetian are the best representative features compared to the outline shape. And here's the comparison between them. In the first paper, they use supervised learning algorithm, but we need to have the disadvantages. We need to have good knowledge about this handcrafted features. In the second one, it's also they got a good performance in the deep learning transfer learning methodology with LR classifier and Swedish data set, but it's a conventional method. They could not, their selection was not optimal. In the third paper, it was they got a good accuracy. They got a good accuracy in the Malaiku D2 data set, but Malaiku D1 data set, it's images of whole leaves, and D2 is the leaf patches, in that they couldn't get a good accuracy. And the next paper being Wang et al., they've got a good accuracy with the inception before structure in the leaf snap. And the leaf snap data sets. And also they have also found out a spatial structure optimizer algorithm in order to reduce, in order to improve the accuracy so as to get a good discriminant features for the similar species images. But that algorithm also not very great improvement was noted from the graph they have shown. And the last one is CNN, and last one they have made use of CNN and deconvolutional layer, and they but it's very complex. That's a disbenefit. And next is the disease detection comparative study. The first paper is Jamie Gracia et al. They have provided a good survey paper on various methodologies used in the disease detection, quantification, and classification. The second paper, it is also 60 experiments were done, and also good accuracy rate also they achieve, but it's very time complex. And the Manish Chandra, he also got good performance in CIMUS network, but accuracy was not up to that mark. And the last one is they have done they have developed this data set their own, and they have done the transfer learning from their own previous model. And the applications this applications of plant species identification and disease detection can be used by botanists, industrialists, food engineers, farmers, and physicians. Conclusion. So here, this paper concludes by presenting general overview of the leaf identification and disease detection process. And here, if you have a less number of data set for training, and if you're going for, if you have an expert if you have a thorough knowledge about the handcrafted features, it is better to go for the conventional machine learning approaches. But if you have a large number of data, and if you're going for don't want to extract features, it's better to go for deep learning technologies. And if you have a less number of data, and then if you then CIMUS network is a better option. And also we have found that MLP multi-layer perceptron logistic regression can outperform other classifiers in the leaf identification. And PC also proved to be improves or maintain the performance metrics. Thank you. These are the references.
Okay, Anu, thank you. This is a literature survey paper, isn't it?
Yeah, this actually I have done during my S3, during my final project, I have done the literature survey, and some testings related to the final project, some I have taken into consideration.
In the graph and all, you have told that VGG 16 is outperforms ResNet and all.
Yeah, and
Have you, can you justify why that performs well? Because of
it's very good. Maybe VGG 16 and all. Maybe
because the
it's
ResNet we usually say that it
They are
is better than human.
but maybe it's I think like this data set, maybe not many images are there. The VGG proves good in many.
Then we can't say like that because ResNet performs well in this VGG.
No, we can very different. It's comparative from the graph. It is very different because if you are there for many complex system, it's okay, but they are skipping the connection and all. But here VGG performs well.
Okay. Anyway, it is a literature survey. What do you mean by dual segmentation?
First, in the identification process, the segmentation is the process where we extract the interesting part from the background. So in the case of disease detection, we need to again segment to get this diseased area. First, we'll.
So, okay, I understand this is a survey paper, but I have a few questions. Just simple threshold segmentation, does it work always? Depends on the background, right?
Yeah, it separates the leaf from the background. Yeah. Simple segmentation.
But there could be different backgrounds and the simple thresholding schemes.
Simple thresholding, yeah. We can, different threshold also is there, adaptive thresholding, yeah, everything.
Yeah, one more thing, when you use the deep neural network, so you put a bounding box just around the segmented leaf and crop it out, right? And resize and give it as input to the CNN. Right?
Yeah, in the final project I have done. This is literature survey. This mostly it's literature survey, some testing only I have done. Yeah, I have resized for the Siemens and all, I have resized to uniform size and then.
I have a question. The Siamese network, like how do you choose a representative sample for each of the classes? How do you choose? One of them has to be the representative sample, the other is a test one, right?
Yeah.
And you look at the how close they are under the L1 norm or the
like for Siemens, I think I took 80:20 ratio. Like
no. When you compare to see whether the test data sample image is nearer to which class.
Okay.
Okay. What sort of leaf it is? Like you have to have some representative samples from the various classes, right?
Yeah.
And you compare that with the test data, and whichever is the closest one, you assign it to that class, right?
Yeah, it is Siemens network. Yeah, when
so
a test data is given, so the Euclidean distance I have.
How did you choose the representative samples from each of the classes? That has to be compared to the test one.
Yeah, I have compared with all the images, training images. I have compared if a test image is coming. I have compared each and single elements from the each classes, like everything I have compared, and will take an average similarity score. Take an average similarity score of each classes, and those class which is having the maximum accuracy will be predicted, will be classified label.
Yeah. So also there's some issue with the figure numbering. If you look at the figure 3, you have put it as figure 2.
Yeah, there was. I understand. I understand some. Yes, I have.
Possible you had to correct it before you publish it.
Okay. Yes, sir.
Okay. From figure 3 onwards, the problem is there.
Yes.
Okay. Thank you.
Thank you, sir.
As you mentioned, you told that this is actually a survey paper. What are the methods that you have tried?
I have tried like PCA. Actually, this is a survey paper for in my.
No, my question is that there are a lot of results that you have shown, graph.
Yeah.
Whether that is the method that you have implemented or.
Yeah, in my mini project. Yeah,
Which platform that you used for implementation? Which
Python.
Programming, Python or not? Python.
Yeah.
Okay. How many test images and training images that you used for that particular?
This is actually from the Kaggle leaf classification feature data set. It contains, I took the ratio in 80s to 20. It contains 990 samples, images.
How many samples?
990 samples total.
For you have mentioned there are multiple databases.
No, the multiple classifiers. I was mentioning about the classifiers.
No, in the first slide, in the block
okay,
diagram, you told
yeah,
that
yeah,
there are many number of databases
yeah, there are many
available.
number of classifiers. So,
which database that you used?
this one. Yes, yeah. In this one, this graph is from the feature data sets of Kaggle, and for
data set of
Kaggle leaf classification data set. It's a feature data set.
No, Kaggle is actually a platform.
Yeah, yeah. In that platform, one data set is available.
Okay, we go to the previous slide.
Yes.
Here you have mentioned the standard data set.
Yeah, images.
Which one? Swedish, Folio, Flavia, LeafSnap?
Yeah, I have used LeafSnap. I have used a manually created one for my.
Manually created means you have created.
Yeah. That was for Ayurvedic herbs. Yeah, that was during my mini project. Yeah.
You have created your own data set.
Yeah, data set of 11.
How many images?
11 classes.
11 classes or 11 images?
No, 11 classes.
How many total number of images?
Total, I think maybe it will be 15 images or something.
15?
Yeah, maybe, yeah, it should be there.
You have taken in your camera?
Yeah, I have taken from my camera, yeah.
That is leaf identification.
Yeah, leaf identification.
Whether you are created for leaf disease detection?
Disease detection also in the final year I have combined model. So I have made use of plant village data set. Yeah. That I haven't taken manually.
Okay, these result from LeafSnap's database.
This is from it is a feature data set from the Kaggle, not the image data set. Whatever the result I have shown in this graph is from a feature data set. So
that you have these results that you have implemented yourself.
Yeah, yeah, I have implemented all these graphs. I have implemented.
Okay, the problem in all the methods that I find is the number of images are very less for especially for deep learning approaches. The number of images should be very high.
Yeah, but I have used Siemens also. So Siemens performed very well compared to.
Okay. Similarly, one more suggestion is that when you are presenting it, try to avoid the literature review after your results. You have given the comparative study, something like that.
Okay.
Reference number 28, 29, 30, 31, 32, 33.
Okay.
Better to include in one table.
Okay. Okay.
Then it will be very easy accuracy database. It is actually time consuming also.
Okay. Okay. This was a literature survey.
Yes, that I agreed. I am saying that when you are making a presentation.
Yes, I will do it.
Okay, thank you.
Okay.
The next paper to be presented is paper ID number 90, copy move image forgery localization using deep feature pyramidal network.
Download ചെയ്യടാ ഇത് ഇത് ക്ലിക്ക് ചെയ്യണം ഡൗൺലോഡ്
Good afternoon. I'm Sabina, presenting copy move image forgery localization using deep feature pyramidal network. The co-authors are Lucy Abraham and Sri Lakshmi here. So these are the outlines. Introduction. We all know that images and videos are used in media, news, advertisement, and medical imaging, criminal investigation, and even as an evidence in law or court. A picture is worth 1,000 words. That means we get more information from a picture or a video clip than a word. That means pictures or image videos have more expressive capability. But due to the availability of the photo editing softwares, one can easily change the content of the image. So digital image forgery is defined as falsely and fraudulently altering a digital image and is a criminal act that provides misleading information about a product or service. So the forgery detection is very important. That is, whenever we use an image as an evidence, it is very important to check the authenticity of the image. So forgery detection techniques are needed for copyright protection and forgery prevention. Types of image forgery. So one of the oldest type of image forgery is the image retouching. In image retouching, some features of the images are enhanced or edited by applying some transformation like scaling, flipping, rotation in order to improve the quality of the image. So it is used by magazine photo editors to improve the quality of the image so that the image looks more attractive. So in image retouching, the content of the image does not change. Whereas in image splicing, some part of the image is copied and pasted to some other part in another image to produce a composite image. So it is also called copy pasting. So the careful splicing will produce a composite image so that we cannot detect any manipulation with an naked eyes. So image cloning, it is also called a copy move. In that case, some part of the image is copied and pasted to some other part in the same image to conceal some useful information. So some post-processing operation like scaling, noise addition, and compression have to be performed on this copied part before pasting it to the original image to make the detection process very difficult. Also, the image, the copied part comes from the original image, and it is very difficult to find the forgery in this type of image. So traditional forgery detection techniques. So normally there are two types of forgery detection. One is the block-based and the second is the key point-based feature extraction and then matching technique. So in block-based method, the image is divided into overlapping blocks of any size and shape, and features are extracted using DCT, DWT, PC, etc. And after that, the features are compared to find out the similar features. So in the key point based method, the entire image is divided, scanned, and the key features are extracted using SIFT, SURF, etc. And then the marked features are detected. So these are the machine learning method. So it uses manual detection of the features. But with the widespread application of CNN in the field of computer vision, we can automatically extract the features. So now that is the deep learning technique is also used in the image forgery detection. So we are proposing a method using deep neural network. So the related methodology that leads to our proposed methodology is copy-move forgery detection using BusterNet. So BusterNet is a two-network architecture that consisting of a mani-det and semi-det. So mani-det is used to detect the manipulated region, whereas the semi-det is used to detect the similarity among this cloned region. So both the mani-det and semi-det consisting of the feature extractor module and a mask decoder module. So so finally, the output from the mani-det is combined using a fusion module to localize the forgery in the image. So the feature extraction of the BusterNet, that is both mani-det and semi-det, uses a feature extraction module that uses a VGG16 architecture. That is the first 4 block of the VGG16 architecture is used. The first and the second block uses convolution layer, 2 convolution layer with a filter size 3 by 3 and ReLU as activation function, whereas the remaining 2 blocks uses 3 convolution layer with a filter size 3 by 3 and ReLU as activation function, and each block is followed by a match pooling layer. So the input to this feature extractor is of size 256 into 256 and the output is 16 into 16. So as the output of the CNN feature is of size 16 into 16 into 512, deconvolution is applied and the features are given to the mask decoder to restore the original size. So in the mask decoder, it uses a BN inception module and a bilinear upsampling module. So that is the BN inception, 3 different convolutions, each with filter sizes 1 by 1, 3 by 3 and 5 by 4 are performed parallelly, followed by a match pooling with the size 3 by 3. So the 3 convolution and match pooling outputs are then concatenated to get the output of the BN inception module. Finally, the upsampling module is used to increase the spatial dimension. So this is the masked deconvolution network of the Buster net. So the input is 16 into 16 size, the output is 256 into 256. So, the disadvantage of this Buster net is that it detects the similarity region accurately, but it failed to detect the manipulated region. So the major contribution. So we are proposing a new methodology that uses feature pyramidal network. So the major contribution in our work is we included a feature pyramidal network to extract the represented tabular features by consolidating the semantically rich low-resolution features with the element from the path layer for distinguishing any forgery in the picture. We also utilized the BGG architecture in the bottom-up path of FPN to extract semantically rich low-resolution features. So this is the block diagram of the proposed methodology, that is the copy move forgery detection with the feature pyramidal network. So feature pyramidal network is a feature extraction module that receives the input signal and produces semantically rich low resolution features as it goes deeper into the network. So it consisting of a bottom-up network and a top-down network. So in the bottom-up network is used for a feature extraction. So it uses BGG16 architecture, that is the first 5 block of the BGG16 architecture is used in the bottom-up path. So the first and second block consisting of 2 convolution layer, and the remaining 3 blocks use a 3 convolution layer of filter size. All uses filter size of 3 by 3 with ReLU as activation function, and each block is followed by a match pooling layer, and the output from the last convolution layer from block 2 to 5 are used as the reference feature map for the top-down pathways. So as it goes deeper into the bottom-up path, the resolution of the signal decreases, but it provides semantically rich features. So the output from the last match pooling layer of the 5th block is again convolved using a 1-by-1 convolution to reduce the channel size, and it is upsampled and it is added with the output from the last convolution layer of the 5th block to get the first feature map M5, and this procedure is continued to the lower block to produce all the feature map. Finally, the features from this top-down path is again given to a 2-by-2 convolution layer with 3-by-3 filter size, and then it is upsampled and concatenated, and finally, in order to detect the or localize the forgery, it is again given to a convolution neural network. In the final layer, it uses sigmod as activation function. So the data set, we use the Common data set for training, testing, and validation of the data set, validation of the model. It consisting of 260 images. Among them, 200 is small scale images, 512 window, that is 512 into 512, and 60 large scale images. So we have performed some kind of augmentation, translation, rotation, scaling, distortion, etc. To convert these 260 images to make a data set of 10,000 images.
One moment.
So there's out of these, the 10,000, 6,000 were used for training, 2,000 testing, and validation, and 1,000 for testing. So these are the performance evaluation. The model is tested using the performance parameters like accuracy, precision, recall, F1 score, and IOU. And these are the obtained values using Busternet and BGG with FPN. So the result indicate that BGG with FPN outperformed the Busternet. And this is the performance metric chart, and this is the model summary information, that is the total number of parameters with the training parameters and the non-training trainable parameters. And this is the result of the Busternet, that is the training and validation accuracy plot of Busternet and the loss plot of Busternet. And this is the training and validation accuracy plot of BGG with FPN and loss plot of BGG with FPN. And this is the result and the original image, ground truth, predicted images. So the result indicate that the Busternet prediction is not accurate, and whereas the BGG with FPN, it provided a better result. So the conclusion, the web offers a new copy move forgery detection network using a feature pyramidal network with VGG net architecture for extracting semantically rich features in the bottom-up path. So the lateral connection is used to add a feature map with the same spatial size from the bottom-up and top-down pathways. According to our evaluation result, BGG with FPN outperform Busternet and many state-of-the-art approaches in terms of accuracy, precision, recall, etc. So extending the work to find forgery and digitally scanned images and video frames is our future plan. So these are the references. Thank you.
In the sample images, which is the forgery you have detected, can you show the sample image, which is the forgery you have detected?
So these are all forged images. That is the original. It is the forged images, and the ground truth is given. That is the where the forgery take place. So that is indicated the ground truth. So the detected result indicate in the image that region is the forged region.
Okay, in the previous one.
The first one, this is the VGB, our proposed method, and the other one is the Bastion method. Bastion method, so that it does not predict accurately. So we are proposing our proposed model, that is the VGG with SPM, it provides better results.
And how do you know that with this from the top-down approach, we have taken one feature data, isn't it? How did you get?
This is the.
Yeah, which layer you have taken that feature data to the top-down layer?
That is the bottom-up part is used for the feature extraction. So that uses VGG 69 architecture. So that output is.
Which are just structured, what is the size of the feature vector?
Feature vector. So that feature vector size that actually so model summary information is not.
Okay,
that size is lower. So in order to increase the upper size, it is, I think it is 8 by 8 into something like that. So it is in order to increase the size, we are giving a again channel size to reducing the channel size. 512 is the channel size. To reduce it to 256, we use a 1-by-1 convolution. Then it is given to upsampling model because the previous fifth convolution layer output is of size 16, channel size 16. So we have to replace that to size of 16 in the 16 size. So that is just we are using the upsampling model.
Then you are concatenated the different features, isn't it?
Yeah, yeah. To get the adding this one, adding laterally to get the feature map. And finally, in order to get 256 into 256, we again give it to convolution network, and then sigmod is used as the activation.
Okay. And what do you mean by BN inspection? The BN inspection you have done what?
BN batch normalization, the full form is. So that also uses a convolution module, that is a module consisting of a 1-by-1 convolution. That convolution is performed parallelly. Finally, these output are concatenated.
Okay.
Thank you, sir.
The next paper will be paper ID number 105, comparison of AlexNet and VGG16 for analysis of plant leaf disease.
Good afternoon, everyone. I am going to present the paper on the topic Comparison of AlexNet and VGG16 for analysis of plant leaf disease.
Please note that your time is 10 minutes.
Okay. So the authors of the paper are Diana Maria Tommy, Aksa Christopher, Alina Jason, Mrs. Harsha A, Aaron Tommy, and Dr. Jason Jacob. Contents. So these are the contents which we'll be seeing further in the presentation. Introduction.
Can you please wait?
Okay.
Some technical issue on our side. Okay. The next paper ID is 105. You have 10 minutes.
Good evening, everyone. I am going to present the paper on topic comparison of AlexNet and VGG16 for analysis of plant leaf disease. And the authors of the paper are Diana Maria Tommy, Alina Jason, Aksa Christopher, Aaron Tommy, Mrs. Harsha A, and Dr. Jason Jacob. So these are the contents which we'll be going to see further in the presentation. Introduction. As we all know, agriculture, which is the most crucial industry in India where most farmers are dependent on. But we know various plants, they are mostly affected by various diseases as well. So it is necessary to detect these diseases at the early stage itself, as it affects the yield that was obtained from these leaves. So various techniques are already available where deep convolutional neural networks will provide a better detection than earlier image processing techniques. So we selected the plant leaf disease detection using AlexNet and VGG16. Objective. Our main aim is to detect the plant leaf diseases using the deep convolutional neural network, AlexNet and VGG16. And also in addition to that, the variation in the accuracy and the training time by changing the number of images on application of learning rate and by applying the freezing of layers was all need to be determined. And to perform the prediction of noisy images as well as to display the remedy for the particular disease predicted. Block diagram. So first stage is image database, then image pre-processing, then training the model, then prediction of disease, and finally comparison of models. Image database, which consists of about 87,000 images of healthy and diseased leaves were there and consists of 30 different classes, and images was downloaded from Kaggle. And from this total data set, about 80% was training set and 20% was validation set. In addition to that, it consists of another directory which consists of 33 test images used for the prediction, and more noises was added by application adding noise to the images and increased the number of test images. Image pre-processing stage. In this stage, we are applying random transformation to the training set where like zoom ranging, rescaling, width shift ranging, height shifting, etc. And the batch size and target size are also fixed at this stage. The next one is training the model, where we will be compiling the model and then we are training the model with the various values of the epochs, and then plotting accuracy versus loss and accuracy versus epoch and loss versus epoch. Next stage is a prediction of disease, where we'll be predicting disease of normal images and noise images and remedy prediction. And finally, the comparison of models. AlexNet architecture. So AlexNet, it is an early successful deep learning architecture which consists of 5 convolutional layers and 3 fully connected layers. So in last fully connected layer, we are provided with 38 units as we have 38 number of class. And in AlexNet is that the convolutional layers, the filter size varies. It will not be the same for the convolutional layers. VGG16 architecture. So we have retained VGG16, which is actually a stacked architecture of AlexNet consisting of 13 convolutional layers, with each layer followed by ReLU activation function. And in the same case of AlexNet, it is having the last fully connected layer with 38 units. And the difference from AlexNet is that in VGG16, each convolutional layers, they're having same filter size as compared to the AlexNet. So this is a training result of AlexNet with a learning rate of 0.001 and 0.05. Okay, so for in the first table, we can see that for epoch 1, the value of the training accuracy was 0.9717. And for the second epoch, it increased to 0.9753. But the third epoch, it decreased to 0.9744. So accuracy should be in a way, it should be increasing as we move on to the moving on to the more epochs, and loss, it should be decreasing. We can see here that the training loss, it decreased from 0.0833 to 0.0786. But when we look at the fifth epoch, it is again 0.0803. That means it increased. So loss should be decreasing and accuracy should be in increasing manner, but that is not the case. So we tried with the different values of learning rate and come up with the learning rate 0.05, where we can see the result and a table where for the epoch 1, the accuracy was 0.9. It decreased to 0.0915. So that was the result of a training result based on learning rate. Next is this is the plot of accuracy and loss versus epoch, where the previous table which we have displayed, where x-axis consists of epoch and y-axis representing the accuracy and loss. It's a graphical representation of the previous table. So this is a training result of AlexNet on freezing of layers, the comparison. That is, freezing is something which we are applying in which the layers will be made from trainable ones to non-trainable ones. So AlexNet consists of about 24 layers, and the 20 layers were freezed. And the result with freezing and without freezing is shown here. So without freezing, we can see for the epoch 5, it obtained a value of 0.9559 validation accuracy, whereas with freezing, it obtained an accuracy of 0.9634. So there is an improved accuracy on freezing as well as decreased loss in the case with when applying freezing. Another observation was that the training time which was required when applying freezing was lesser as compared to compared with training without freezing. So this training result of VGG16. So here VGG16 obtained a training accuracy about 0.9254 and validation accuracy about 0.9351 at the fifth epoch. And the plot of this is shown in the right side as well. So this is the improved training result of VGG16. So what we did was the last three, like it consists of different blocks of convolutional layer. The last block of the 3 convolutional layer and the max pool layer, they were made trainable ones. And we added 2 fully connected layer with 4096 neurons with dropout of 0.25 and also added batch normalization layer. And we trained it for 8 epochs and got an improved accuracy about 98, validation accuracy about 0.98 at the 8th epoch. This way, we obtained an improved training result of VGG16. So this is the disease prediction of noisy images, where in the first row, we can see Apple said arrest with the PSNI value 28.6025, which was predicted by AlexNet and VGG16. So the indication of the PSNI value is that if higher the PSNI value, which means that the image quality is higher, which means it consists of lesser noise. So we can see in the second image, the same Apple said arrest, but it consists of more noise. As we can see, the PSNI value, it is decreased one as compared to the previous one, 28.60. From there, it is 28.27. So which was not predicted by AlexNet and which was predicted by VGG16. So similar cases we have tried with many other images as well. For potato early blight, the result is shown with a value of 29.465 PSNI value. It was predicted by both the models. And when we added more noise, it was not predicted by AlexNet while it was predicted by VGG16. So these are the other results of corn common pressed and tomato healthy leaves as well. So the conclusion which we have got from here is that the PSNI value with 28 and above was predicted by VGG16, whereas from 28.5 and above was only predicted by AlexNet. But there is only slight variation in that. So next is disease prediction with remedy. So along with predicting the disease name, we have added the disease remedy as well. So in the case, we can see the output for tomato yellow leaf curl virus. It was given with the remedy as maintain good weed control and prevent whiteflies to healthy plants. And for another image of tomato yellow leaf curl virus is also shown. Then another one is the corn common rust, which was provided with a remedy that uses spraying with fungicide and uses more corn that is resistant to the fungus. And another image of apple cedar rust is shown, with which is provides the remedy as we can treat it with a solution of copper at least 4 times, uses a 0.5 to 2 ounces of copper per gallons of water. And for potato early blight, using fungicides like mancozeb and chlorothalonil, and to provide sufficient aeration between the plants to allow the foliage to dry, etc. So conclusion. So we have compared the models based on different parameters like accuracy, then prediction of the noisy images. So the basic difference is in the layer where AlexNet model, which is consists of 5 convolutional layer, VG16 consists of 13 convolutional layer. So as AlexNet model, which is lesser deeper, it took only lesser training time as compared to VGG16. Then we have tried with 10 number of classes in order to know what happens when number of images decreases. And we in both the cases, when the number of classes 38, that is, it consists of more images, both of them produced more increased accuracy. And AlexNet model predicted images with the PSNI value 28.5 and above, whereas VGG16 was able to predict PSNI value 28 and above. Finally, we can VGG16 with the highest accuracy of 90% perform better detection of disease. Thank you.
Thank you, Elena. This is a comparison study, isn't it, with AlexNet and VGG16? You have taken some data set.
Yes.
How did you predict the remedy? That is also from the data set, or you yourself manually predicted the remedy?
We have inputted this a text file with the disease name along with that particular remedy, and we give a code after the prediction.
Along with the particular remedy means from where you get the remedy?
Like we search from network, internet, and for this particular disease, what will be the remedy?
It is automatically predicting the remedy or
no, like if this is the disease, then it will be predicting this remedy. Likewise, we gave it likewise.
You have created a table in the program. Huh?
Sorry, ma'am.
You yourself have created a lookup table by searching the net. You yourself created the data set.
Yes, ma'am.
Predict here. Okay. Can you tell me why, you justify why freezing reduces the training time?
Because, ma'am, that is actually we can apply freezing to the pre-trained model. So basically, this AlexNet VG16s are pre-trained models where their layers have already been trained. So there is no need to retrain again this. If we apply the freezing, it will be like they're already trained ones. So it will be wastage of time that we are taking more time to pass it to the all layers and making the updations. So it will be obviously it will reduce the training time.
Then what you have done for this? What is your contribution? This is already a comparison, isn't it? Have you done any contribution to this paper?
Yes, ma'am. This analysis and all are our contributions. Like what will happen if we apply freezing and then varying with the learning rate of the results, and then prediction by using noisy images.
Hello. Which data set did you use?
A data set from Kaggle, sir.
Kaggle. Okay. I have one more question. You could also have predicted the severity of the disease, right? For various diseases.
Yes, sir.
You could use some regressor for that?
No, sir. We didn't check on that. Like we didn't focus on like how much severity.
Okay. And one more thing, like that solution which you gave for each of the disease, like for each disease, against that you had a like solution, right, as to how to treat the plan.
Sir, yes, sir. Sorry, sir.
Okay, okay, it's fine.
Okay.
Thank you.
Thank you, sir.
The last presentation for the day will be presented by paper ID number 17 on the topic YOLO V5 based open source UAV for human detection during search and rescue, SAR.
I downloaded the presentation video. Oh, okay. Please note that you 10 minutes.
Good evening, all. I'm Manal, and I'm one of the authors of the paper YOLO V5 based open source UAV for human detection during SAR. I'm here on behalf of all the other authors of the paper, Shruti MS, Nandana VN, Lakshmi S, Mohammed Shamshad, and Sudesh VS, to present our paper at this conference. Abstract. So if manual search and rescue is done, then there's a difficulty because the search and rescue will be done slowly because of the difficulty in identifying human presence. So our paper is trying to propose the use of a quadcopter for real-time monitoring of isolated places and automatically detecting the location of the humans and using image processing techniques at affordable rates. Novelty. So this paper is based on a project we did, and the project is one of the first few drone applications of the latest YOLO V5 object detection algorithm, and we have used it for real-time human detection. Then our prototype uses open source hardware and software tools. We have used open source autopilot module, APM 2.8 flight controller, and we have used YOLO V5 object detection algorithm, which is also open source. So since we have used open source tools, it is a more economically viable option. Then the algorithm was trained on a custom dataset of over 1,000 images taken from different orientations, and we could attain MAP of 0.954. Introduction. So during natural catastrophes like floods, aerial surveillance has an advantage because we can get real-time information from them because they can survey the area. And if we incorporate drone technology, computer vision, image processing, and all with aerial surveillance, it will be advantageous because we can get provide quick response and save human lives. So that is what we are trying to propose through this paper. Contributions of this paper are practical implementation of open source drone for search and rescue during natural calamities, quick and efficient real-time monitoring of calamity affected areas, detection of stranded human beings using YOLO V5 object detection algorithm, sending GPS coordinates of detected humans via mail for speedy response, and also visualization of the detected humans on map, which will also help in rescue. Then mini survey results of flood-prone area of Kerala, reflecting on the total time taken by calculating the total time taken by them. Methodology. Block diagram of the system. So there's a drone block and ground control station. The quadcopter is a primary component, and the camera and video transmission system on the quadcopter lets us get the real-time video. So it is sent to the ground control station, and in the ground control station, human detection code is run. GPS location extraction and mapping and all are done in ground control station. And from there, mail is sent to respective authorities. The drone block can be explained better with the connection diagram. As I mentioned earlier, we use APN 2.8 flight controller. It is powered with the 11.1 volt LiPo battery, and it receives PWM signals from the 6-channel RC receiver. And these PWM signals are given to the 4 BLDC motors via electronic speed controllers. We also have telemetry module and GPS module working. So this flowchart shows the overall working of the project. First, we power the quadcopter with our LiPo battery. Then we arm our quadcopter with the help of the RC controller. And then we start the human detection program in the ground control station. If the drone is connected, then we'll be receiving real-time video and image processing will be done on it. So after the video is obtained, real-time video is obtaining, we'll start maneuvering the drone over areas to be assessed. And if a human is detected, bounding box is drawn over them, and the GPS coordinates of the detected human will be stored in a database. And after the assessment is over, we'll land the drone, disarm the quadcopter, and in the end, a map will be generated which has the location of the people pinpointed, and mail is sent to respective authorities, mail containing the location. Hardware, this is the quadcopter we built. We can see the RC controller and all the components we used. Dataset development. So for the dataset development, we took images from our drone footage, and there were 1,028 images we used. And we only have one class, humans. Humans are different orientations and all were captured. And we did annotation in RoboFlow. We can see an annotated image in the slide. Human detection. The program uses model trained on custom dataset using YOLO V5 algorithm. So when the human detection program is run on the ground control station, predicted bounded boxes are drawn over the frames extracted from the camera feed, and the footage containing the detected results are stored in a directory. YOLO V5. This is the algorithm we used. It is a latest version of YOLO, You Only Look Once, which is an open source and real-time object detection system. It has unique features like mosaic augmentation, 16-bit floating point precision and all, which helps it have better inference speed and accuracy. So that is important for a project like us, which has real-time detection. YOLO V5 training. You can see a snapshot of the training. We did training in GPU Tesla V100, and it took around 6 hours. The training results. So here in the precision recall graph, we can see that we achieved an MAP of 0.954, and we could achieve an F1 score of 0.92 at 0.489 confidence score. Then these are the graphs, precision versus confidence graph and recall versus confidence graph. Mission planning. These images are the projection of the camera footage. I can explain it better in the next slides. So for mission planning, the speed is the major determinant factor that determines the flight time and accuracy. Maximum speed of the drone will depend on the type of camera used, the processing time of the ground control station, and the percentage of overlap. And the processing time depends on image processing time, image detection time, and frame rate of the video feed. And to determine the speed, the ground footprint of the drone must be found. So we have set the drone camera at an angle of 45 degrees. This image shows the field of view of the camera. This is the projection on the ground. It is a trapezoidal image, trapezoidal projection, but only the rectangular part will be considered because that is a part without distortion. Then this image is the overlap between two images. Overlap is basically the common area. The shaded portion shown is the common area between which is common area in the simultaneous two images in the same flight line. We chose as 80% for this calculation, so obtain a smooth video. And after calculation, our processing time was 0.47, and our maximum speed was calculated to be 27.31 meter per second. Hence, a safe speed of 10 meter per second was chosen. Mission planning. So, mission planning, Planner is a free and open source software used to plan missions. We did survey in, utilize the survey feature of Mission Planner. A portion of our college, Government Engineering College Thrissur, was considered for the survey. And this setup will take approximately 10 minutes and 54 seconds to fully cover an area of 8.92 acres when flying at an altitude of 8 meters at 10 meter per second speed. Then second service was done on an extensive area of Thrissur town. For this, we used a better camera. The camera we have is Foxy Razor Mina camera. For this, we use GoPro Hero 4 wired camera. And for the setup, the area is 1,351 acres. And it will cover this, with the setup, it could cover cover in 1 hour and 31 minutes at a speed of 15 meter per second and an altitude of 100 meter. And so such large area can be covered during a rescue mission by making into smaller areas of flight times of 10 to 15 minutes for faster SAR operations. Results. So the first image shows the program deployment. The first image is the program running behind, and we can see the GPS coordinates printed on the console. And the next image, the image detection, that screen. And you can see the humans detected. Then this image shows the email sent to the rescue authorities. We tested it, we're sending it to a mail. And the next image shows the digital map created, pinpointing the location of the detected people.
Please note you have 1 more minute.
Okay. I'm sorry, the video isn't playing. I'm sorry, the video isn't playing. So the video showed the video saved from in the directory of the detection, and this video is supposed to show the maneuvering of the drone done. It's not playing in the system. Sorry. Conclusion. This paper presents a drone-based approach for human detection for SAR operations, and we use YOLA V5 for on the custom data set created from a footage taken from our camera on the drone. A live video of the disaster area is obtained via radio telemetry. The location of the detected humans are pinpointed on a digital map and also sent to the respective authorities via mail. We used open source hardware that makes it economical, easier to build and reproduce. Future scope. So using cameras like GoPro can widen the search area, as I explained in the second survey, by flying it at higher altitudes. Also, such a setup will aid in creating better data sets, which will make the SAR operations better. Then if the drone is made completely autonomous, it will have more accuracy. Then IR and TIR cameras can be incorporated to use so that we can detect even in areas where there's this destruction. I mean, things like trees and buildings and all. References. Thank you.
Thank you. Yes, Shruti.
Manal.
Okay. You used this quadrangle video to detect human being, isn't it?
Real time, yeah.
Real-time human being using the YOLO V5.
Yeah.
Okay. And then you send the data via mail.
Yeah. The program
image or the location.
The location is stored in a database, which is sent. A CSV file is sent. We can see it here. Yeah, a CSV file is sent.
The location or the images.
GPS location, yeah.
GPS location you send via
mail.
Okay. Then what is your contribution? That is, this drone is developed by whom? Research assistants. Who developed this drone?
The research assistants, it is our final year project, and we were selected when we sent our project proposal. We were selected to use the facilities in IC4 Trivandrum. So they are the research assistants who work there, and they helped us out in building. We were the ones who contributed economically, the money and all we put, and we did the thing. They over there, they helped let us use the soldering and all those facilities over there, and they have worked in drones, and also they guided us when we made errors and all.
Okay.
So your camera was positioned say 45 degrees or something,
Yeah.
right? Then when the altitude changes, okay, the
yeah.
altitude of the drone, it changes the perspectives of the various humans. That also changes, right? So won't that lead to some loss of accuracy when you detect using the YOLO V5? For example, the training data might be on some data images which you obtain while flying at 10 meters or something.
Yeah.
And later, if you fly at 100 meters altitude, then
Yeah, so right now our drone isn't autonomous. We have an RC controller and we are flying it at 8 meter per second. Sorry, 8 meters height only. And we had the data set created also was at 8 meters height. Right now, we are using such a prototype because of a money constraint. We build a prototype only, not a very good drone.
So in all the test data, test runs, it could detect all the human beings, is it?
Yeah, actually the video isn't playing over here. Yeah, in this image you can see, yeah, this, actually the video isn't playing in the system. I'm sorry, but I don't know why. The video isn't
That's
playing.
fine. When there are some natural calamities,
Yeah.
then the background will be different. Like, will that create some issues with detecting the humans?
That is for the data set we could only create it. We did it in the beginning of this month just before lockdown. Sorry, beginning of this year. And at that time we could only create a data set with plain land. But we did in different areas, but it was plain land only. We couldn't test it in real. I mean, make data set in real flood conditions.
Okay, really good work.
Thank you, sir.
Okay. Thank you.
Thank you, sir. Ma'am. Now I request Dr. Abraham Thomas, Professor of Applied Electronics and Instrumentation Department, to hand over the certificate to our session chair, Dr. Binsu Kovo.
Binsu Kovu for doing an excellent job as the chair of this session on image processing.
So now we have come to the end of today's technical session. The next keynote session will start in the same hall tomorrow, sharp at 9:30 a.m. Kindly make yourself available before time to avoid any delay in starting the session. Thank you all for your participation.